Chapter 24, Probability and Statistics, Section 24.1, Basic Probability Theory. There are two types of probability distributions: discrete probability distribution versus continuous probability distribution. In a discrete probability distribution, the number of possible events or outcomes is countable. We can count individual outcomes. In a continuous probability distribution, the number of possible events is uncountable. The discrete probability distribution can be illustrated with a bar chart. We cannot do that for a continuous probability distribution. Here are some discrete examples, like throwing a die, drawing a card, or tossing a coin. When we throw a die, there are 6 possible outcomes from 1 to 6. When we draw a card from a deck, there are 52 possible outcomes, excluding the jokers. When we toss a quarter, there are 2 possible outcomes, heads or tails. Now let's throw 2 dice. There are 11 possible outcomes from 2 to 12. Well, to get a total value of 2, the probability is really small. It's only 1 over 36. Roughly 3%, because we need both dice to be 1. Therefore, it's 1 over 6 times 1 over 6. The probability of getting a 12 is larger. It's not even larger. It's also 1 over 6 times 1 over 6. It's 1 over 36. Only because to get a 12, you need both dice to be 6. Alright, therefore you have a very small probability over here, 1 over 36. What's the probability of getting a 3? Well, it's different, because this time when we threw 2 dice, it can be 1 and 2, or it can be 2 and 1. So the probability is 2 times 1 over 6 times 1 over 6. It's 2 over 36, a bit larger. What's the probability of getting a 4? Well, you could get 1 and 3, 2 and 2, and 3 and 1 out of this 2 dice. So the probability is 3 times 1 over 6 over 1 over 6. It's going to be 3 over 36. The probability reaches the maximum if the sum is 7, because to get a 7, you have many different ways. You can have 1 and a 6, you get 7. 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1, you get 7. So the probability of getting 7 is 6 over 36. We have 6 different ways. What about the probability of getting 8, 9, 10, or 11? Well, the probability starts to decrease. It's 5, 4, 3, or 2 over 36. And when we sum up all those probabilities of all possible outcomes, it should be 1. You can verify this. This is the probability of getting a value of 2 from 2 dice. 3, 4, 5, 6, 7 maximum. Alright, and then 8, 9, 10, 11, 12. If you sum it up, you get 1. Now let's look at the expectation value of throwing just 1 die. It's 3.5, because you may get 1 or 2 or 3 or 4 or 5 or 6. You take the average, 3.5. What if you threw 10 dice? The sum is going to be 35 plus minus some deviation. The average is going to be 35 when you threw 10 dice. If you threw 10 dice 1 billion times, alright, and then look at the distribution, you'll see the probability is maximized at 35. That's the expectation value of throwing 10 dice. Now let's look at some poker cards. When we draw 1 card out of a deck, the probability of getting an ace is 4 out of 52, because we have 4 different aces. We have ace of diamonds, ace of hearts, ace of clubs, ace of spades. So when you draw 1 card out, well, there are 52 outcomes. Out of this 52 outcomes, 4 are desired outcomes. Now let's draw 2 cards. What's the probability of getting an ace and a king? Well, it's more complicated. First, we draw 2 cards. What's the total number of possible outcomes? Well, it's 52 times 51 over 2 factorial. Why that? The first card you have 52 different options. Second card, only 51 options left. So it's got to be 52 times 51, right? But then you need to divide that by 2 factorial, because, if you get 2 cards, if you get A and then B versus B and then A, we consider this 2 the same outcome. We count A and B or B and A as one single outcome. So we need to divide that by 2. More accurately, we need to divide that by 2 factorial, because when you have 3 cards, you can have 3 factorial different orders. So you can have ABC, ACB, BAC, BCA, CAB, CBA, 6 possible different orders. But we count them as one possible outcome. So we need to divide those by 3 factorial. So get back to this. What's the opportunity of getting 1 ace and 1 king? So when we draw 2 cards, there are many possible outcomes. Over here it's 52 times 51 or 2 factorial. Alright, this many possible outcomes. 16 are desired outcomes, because we can have 1 card being one of the 4 aces, and another card 1 out of 4 different kings. So 16 different desired outcomes. So you can have A of diamonds plus king of diamonds, A of diamonds and king of hearts, A of diamonds, king of clubs, A of diamonds, king of spades. And then A of hearts, king of diamonds, A of hearts, king of hearts, A of hearts, king of clubs, A of hearts, king of spades. So you can just get 16 different outcomes that correspond to 1 ace and 1 king. What's the probability of getting 2 aces? Well, that's going to be smaller, because again, this is the total number of outcomes of drawing 2 cards. And now let's look at the number of outcomes with 2 aces. There are only 6, because you can get A of diamonds plus hearts, A of diamonds plus clubs, A of diamonds and spades, A of hearts and clubs, A of hearts and spades, A of clubs and spades. So only 6. Only 6. Alright, why? Because there are 4 suites. The first one you have 4 options, the second one you have only 3 options left. And we're looking at only the combinations. We don't care about the orders, so we need to divide this 2 factorial different orders. We have only 6 outcomes. Now when we draw 2 cards, what's the probability of getting 2 cards of the same rank? It's only 3 out of 51, just because whatever the first card is, out of the remaining 51 cards, only 3 have the same rank, so it's 1 over 17. Alright, so we just do 3 divided by 51 is 1 over 17. There's another way to calculate this. Over here on the bottom, that's the total number of outcomes of drawing 2 cards. Alright, 52 times 51 over 2 factorial. Now, the possible outcomes. Alright, 2 cards of the same rank, how many are there? There are 13 ranks, so we have 13 times over here. Within the same rank, the first card you have 4 options, second card 3 options only, and then divided by 2 factorial, and then you do this calculation, you'll get the same number, 1 over 17. Alright, now let's draw 2 cards again. The probability of getting 2 cards of different ranks is 16 out of 17. Why is that? Whatever the first card is, out of the remaining 51 cards, there are only 48 cards with a different rank, right? So it's going to be 48 over 51. It's 16 over 17. Also, you can just look at this 2 paragraphs. Here, 2 cards of the same rank. Here, 2 cards of different ranks. Well, they complement each other. So the probability of getting 2 cards of the same rank versus the 2 cards of different ranks, if you sum them up, it should be 100%. So 1 minus 1 over 17, you get 16 over 17. When drawing 3 cards, the probability of getting all 3 cards of the same rank is this. Alright, this is the total number of possible outcomes of 3 cards. 52 times 51 times 50 over 3 factorial, because we have 3 factorial different orders, or so-called permutations. On top, you have 13 ranks. Out of each rank, the first card 4 options, the second card 3 options, 2 options over 3 factorial. And also you can just see, if you choose 3 cards out of 4 cards, there are only 4 options. It's just the you have another way of thinking about this. You need to pick a card and do not choose it. Alright, so 4 options as well. So 13 times 4 here divided by the total number of outcomes. That's pretty small. It's 1 out of 425. Now what if you draw 4 cards? Alright, you draw 4 cards. And the probability of getting all 4 cards of the same rank is even much smaller. Alright, because you have only 13 desired outcomes. You get 4 2s, 4 3s, 4 4s, 4 5s, all the way to 4 aces. On the bottom, you have this many different outcomes. You do the calculation. It's 1 out of 20,000. You can try this. You can try this all day and see how many times you get 4 cards of the same rank. Very slim chances. In general, the total number of possible outcomes of drawing m cards out of n cards is this. Okay, n factorial over m factorial over n minus m factorial. If the order of drawing those cards does not matter, we're going to count all these 6 different orders as one combination. Alright, so ABC is equivalent to ACB, equivalent to BAC, right? So when you play like blackjack in a casino, whether you get a ace and then a king, or a king and then an ace, I mean, that's just the same. But what if you draw m cards out of n cards, and what if the order matters? Well, if the order matters, then there are m factorial permutations. Alright, if you have m cards. So if you have 3 cards, you have 6 permutations, or 6 different orders. When you have 4 cards, you have 4 factorial permutations, or 4 factorial different orders. Alright, when you have 4 cards, or just let's say 4 objects, A, B, C, D. So you can have A, B, C, D, you can have A, B, D, C, A, C, B, D, A, C, D, B, A, C, B, D, A, C, D, B, A. I think I lost track. But in total, you will have 4 times 3 times 2 times 1, a total of 24 different permutations. Okay, so when you have A in the front, you have 6 permutations. When you have B in the front, you have 6 permutations. When you have C in the front, you have 6 permutations. When you have D in the front, you have 6 permutations. So in total, you have 4 times 6, 24 permutations. What if you have 5 different objects, A, B, C, D, E? And then you can have either A or B or C or D or E in the front. So you have 5 options. Alright? And for each such option, you have 4 factorial different permutations. So if you have 5 objects, you have 5 times 4 factorial permutations. 5 times 4 factorial is 5 factorial. So you have 5 objects, 5 permutations, 10 objects, 10 permutations. Alright? Alright, so the number of permutations can be much larger than the number of combinations. How much larger? Well, it's just m factorial larger. Alright, so if you see this expression and this expression, they differ by a factor of m factorial. Now let's look at some numerical example. Problem 24.1. Calculate the number of combinations of drawing 6 cards out of 10 cards. Calculate the number of permutations. So I'm going to just use these 2 equations. Number of combinations 10 factorial over 6 factorial over 4 factorial 200. 10. Number of permutations. Wow, this is going to be larger because for every single combination there are 720 permutations. 6 times 5 times 4 times 3 times 2 times 1, that's 720. So these two numbers differ by 720. 210 times 720, you get a number greater than 150,000. Such a large number of permutations when you just draw 6 cards out of 10. What if you draw 6 cards out of 10 cards? Alright, drawing 10 cards out of 10 cards. Alright, you have only one combination, right? It's going to be 10 factorial over 10 factorial over 0 factorial. 0 factorial is 1, and you get just one combination. The number of permutations, a lot. It's going to be 10 factorial. Alright, 10 factorial is this 6 factorial times 7 times 8 times 9 times 10. It's a huge number. Now let's toss coins. When we toss 2 coins, there are 3 possible outcomes. 2 heads, 1 heads, 0 heads. In terms of the number of heads. If we don't care, which coin is heads, which coin is tails. So when we see this 1 heads, actually you may ask, if you have 2 coins, which coin is heads, which coin is tails? Well, if the 2 coins are somehow like quantum coins, indistinguishable quantum coins, and then you have only 3 outcomes. But if you have real coins, like real quarters, right? If you threw 2 quarters, you know which is which, and then you get 4 different outcomes. You get heads heads, heads tails, tails heads, tails tails. All right. And the probability is it depends. It's 25% here, 25% here, 25% here, and 25% here. But if my question is about the probability of getting 2 heads, 1 head, 0 heads, it's just 25, 50, and 25%. Now, what if we rig the coins? And to make them with 60% chance of heads, 40% of tails, just to make money illegally, and then we can calculate the probability differently. So let's say we have n coins. We toss n coins, and let's calculate the probability of getting I heads. There's an equation over here. The equation is this. It's going to be n factorial over I factorial over minus I factorial. So when you look at this, you probably realize this is the number of combinations of selecting I cards out of n cards. Now we're just selecting I coins from n coins. Alright, after you make the selection, all this I coins should be heads, and that's the corresponding probability. The remaining n minus I coins should be tails, and over here that's the probability of all these coins with tails. So that's why we have this formula, and we plug in numbers. Alright, so what if we are again tossing 2 coins? The probability of getting 2 heads, we plug in 2 here, 2 heads, we plug in 2 here, and then 2 minus 2, 0.6 to the power of 2, and this is 0.4 to the power of 2 minus 2, so all this done, 0.36. 0 heads, 0.16. In the middle, 0.48. You just do this. Well, we can verify this really easily. You have 2 coins, right? Both are heads. Should it be 0.6 times 0.6? 0.36. What's the opportunity of getting 2 tails? Well, 0.4 times 0.4 over here. What's the probability of getting 1 heads? Well, it's just 1 minus this minus this. You get 0.48. So we can easily verify this. But why don't we just do 60% times 60% here? Instead, we did this. I just want to show you a systematic way of computing the probability with rigged coins. What if we have 10 coins and we need to calculate the probability of getting like 6 heads out of 10 coins. And then you need to use the formula. It's going to be 10 factorial over 6 factorial over 4 factorial times 0.6 to the power of 6 times 0.4 to the power of 4. And then you can get a number at least. 2 coins is really simple, but when you get 10 coins, and we need 6 heads out of 10 coins, you need to use this equation. When we toss 3 coins, there are 8 possible outcomes. If the coins are distinguishable, if you have real quarters, you know which is which. There are 8 possible outcomes. But if those are quantum coins, like electrons, they are indistinguishable. There are only 4 possible outcomes. 0 heads, 1 heads, 2 heads, 3 heads. That's it. 4 possible outcomes. When we toss n distinguishable coins, there are 2 to the power of n possible outcomes. But if those coins are indistinguishable, we have only n plus 1 possible outcomes. From 0 heads all the way to n heads, there are just n plus 1 different possible numbers of heads. What if we toss 1 mole coins? Well, we get many outcomes. It's 2 to the power of 1 mole possible outcomes. What if all those 1 mole coins are indistinguishable? Then we have just 1 mole plus 1 possible outcomes, because we can have 0 heads, 1 heads, 2 heads, all the way to 1 mole heads. Again, there are 2 different types of probability distribution: discrete versus continuous. Now let's talk about continuous probability distribution. Yeah, continuous probability distribution, the number of possible events or the number of possible outcomes is uncountable. And also, between any 2 outcomes, there are an infinite number of outcomes, different outcomes between just any 2. Here, let's look at one example. If I know a particle is between 0 meters and 1 meters, right? And there are many outcomes, actually an infinite number of outcomes, right? You can have the particle at 0 meter, you can have the particle at 1 picometer. Between 0 meter and 1 picometer, you still have an infinite number of outcomes, right? You can have like 1 femtometer, 2 femtometers. And even between 1 femtometer and 2 femtometers, you can have like 1.1 femtometer, 1.2 femtometers, right? So you have an infinite number of outcomes between just any 2 different outcomes. That's continuous. So that's why we cannot simply display the continuous probability distribution with a bar chart. We have to use the probability density curve. Alright, something like this. And the horizontal axis is just the possible outcomes, and we have a continuous distribution of possible outcomes. The vertical axis is the probability density. Here are 2 examples. One example is from quantum chemistry. The probability density of finding the electron at radius r in the hydrogen atom is this. Alright, it's the squared modulus of the wave function times r squared. The probability from r to r plus dr is the density times dr times the range. Alright? To have the probability, you need to multiply the probability density with the range. In this case, the range is dr. Another example, the probability density of a speed in the x direction is proportional to this. This is from chemical kinetics, the kinetic theory of gas. So if you have gas particles moving around, the probability density is proportional to this, e to the power of negative kinetic energy over kBt. And we're focusing on the x direction. All right. So there are 2 examples about continuous probability distribution, and in that case we need to visualize the probability density. Okay, we cannot visualize probability. Now here's some discussion about the probability itself. The probability of finding the electron in the hydrogen atom at any radius is just exactly 0, because you need a range to get a non-zero probability. Alright, if you have a range from R1 and R2, let's say from 0.8 angstrom to 0.9 angstrom, and then you can integrate the probability density and you get a finite value, which is the probability of finding this electron within a spherical shell between the radius 0.8 angstrom and 0.9 angstrom. So you can do that. What if you have a range from 0 to infinity? Of course it's going to be 1. That means the probability of finding the electron in the entire space. Actually, when you see this, that means the entire universe. Well, it's just 100%. The probability density of speed in the x direction can be normalized. This is not normalized. It can be normalized. If you integrate this from 0 to infinity to be 1, I mean, it can be normalized. You just need to evaluate this integral. We have this n as the normalization factor. Alright, you just ensure over here, the total probability of finding the particle with a speed between 0 and infinity is 1. So you just need to do that. Alright, over here is just a graph of this probability density. Alright, for the electron in the hydrogen atom, it's just this. It looks like this. The probability density of speed in the x direction is proportional to this, and we can normalize it. We just need to set it to 1. If you know how to integrate this function, you will see n is the square root of 2m over pi kbt. We do this kind of derivation in chemical kinetics. The normalized probability density is just this, the normalization factor times the exponential function of negative kinetic energy over kbt. What about velocity? The normalized probability density of velocity is actually 1/2 of this. You can see when this is divided by 2, this 2 disappears on top from the top, appears on the bottom, because I just divided this normalization factor by 2. Because the velocity is sine. So if you have a speed of 1 meter per second, the velocity can be negative 1 meter per second and positive 1 meter per second. They share the same speed, so I need to divide this by 2. And on top, I should have this negative m velocity squared over 2 kbt. But it turns out this squared is the same as the speed squared. Alright? Because negative 1 squared is also 1. The probability density distribution of the one-dimensional velocity is a Gaussian function. Okay, for velocity, it's going to be a Gaussian function, bell shape. It looks like this. And if you integrate the normalized probability density for velocity, so if you do this from negative infinity to positive infinity, you'll get 100%. The physical meaning is simple. The probability of finding a gas particle moving at a speed between negative infinity and positive infinity in the x direction should be 100%. Please note the difference between speed and velocity. Chapter 24, Probability and Statistics. Section 24.2, Configurations and Microstates. When 3 energy quanta are shared among 3 molecules labeled A, B, and C, there are 10 possible microstates and 3 possible configurations. So we can see A, B, C can each get 1 energy quanta. Also, they can get 210, 201, 120, 021, 102, and 012. They can also get 300, 03, 0003, respectively. So we can see there are 10 different possible ways of allocate the 3 energy quanta among 3 molecules. They are called 10 possible microstates of this system that consists of 3 molecules with 3 energy quanta. Also, we define configurations this way. There are 3 possible configurations. The yellow configuration, we have 1, 1, 1. The green configuration, we know one of the 3 molecules contains 2 energy quanta. One molecule contains 1 energy quantum. The third molecule gets nothing. That's our second configuration. The third configuration corresponds to just one molecule having all 3 energy quanta. So over here from this table we see 10 rows. They correspond to 10 microstates. They can be grouped into 3 possible configurations. Assuming a molecule dissociates when it absorbs 3 or more quanta of energy, we can use this table to calculate the probability of finding a molecule dissociates in this system. Because we look at all 10 microstates, 3 correspond to a molecule having 3 or more energy quanta. That means this 3 microstates correspond to the dissociation of one molecule. 3 microstates out of 10 microstates. That means we have 30% probability of finding a molecule dissociates in this system. What if we have 4 energy quanta shared among 3 molecules? Well, this time we have 15 microstates. Well, we can have 4, 0, 0, 0, 4, 0, 0, 0, 4. And we can have 6 different permutations with 3 and 1 and 0 energy quanta attributed to the 3 molecules. We have 3 permutations here in yellow. They correspond to 2 molecules, each getting 2 energy quanta. And over here are also 3 permutations that correspond to 2 molecules, each getting 1 energy quantum. So we have a total of 15 microstates. We have only 4 configurations, however. They correspond to 400, 310, 220, and 211. By ignoring all those permutations, when you have 310, there are 6 combinations, but there are 6 permutations, but only 1 combination. The number of microstates of these 4 different configurations are 3, 6, 3, and 3. So 3, 6, 3, and 3. We sum it up, we get 15. When 5 energy quanta are shared among 3 molecules, there are 5 configurations: 500, 410, 320, 311, 221. The number of microstates are 3, 6, 6, 3, 3. So you can see if all 3 numbers are different, like in this situation 3 and 2 and 0 are different, you get 6 permutations. Over here 410, this 3 numbers are different, you get 6 permutations. And over here in 500, 2 numbers are the same, so you really just need to pick one molecule to receive the 5 energy quanta. We have 3 permutations. So that's why we have this number of microstates associated with these configurations, and we sum it up, we get 21. What if we have 6 energy quanta shared among 3 molecules? Well, we can have 600, 510, 420, 411, 330, 321, 222. And then we can compute the number of microstates. Usually they are 6 or 3. When the 3 numbers are different, you get 6. When 2 of the numbers are the same, you get 3. Over here, all 3 numbers are the same, and then this configuration, well, it's associated with only 1 microstate. It has to be just 2 to 2. We sum it up, we get 28 as the number of microstates when 6 energy quanta are shared among 3 molecules. Now we can also ask a question, what if a molecule dissociates with 5 or more energy quanta? And then we can see over here, we have 3 microstates, 600. We have 510, 6 microstates. So total, we have 9 microstates in total with 5 or more quanta. So we have 9 different microstates out of 28 microstates. A bit more than 30%, you see a molecule dissociates. In general, when m energy quanta are shared among m molecules, the number of microstates is this. I'm giving you the formula here. We will prove this later. It's m plus n minus 1 over m factorial over m minus 1 factorial. So both m factorial and m minus 1 factorial are on the bottom. For example, if we have 6 energy quanta shared among 3 molecules, the equation is this: 6 plus 3 minus 1 on top, factorial on top, 6 factorial on the bottom, 3 minus 1 factorial on the bottom, and really it's just 8 factorial over 6 factorial over 2 factorial, and 8 factorial over 6 factorial is 8 times 7, so we have 8 times 7 over 2 factorial, that's 28. When a fixed number of energy quanta are shared among more particles, the number of microstates increases. The number of configurations usually increases. So let's look at a few examples. When 4 energy quanta are shared among 3 molecules, we learned there are 4 configurations, and we have a total number of 15 microstates. Alright, we can just use this equation now. M is 4, N is 3. We plug in the equation, we get 15. What if we share 4 energy quanta among 4 molecules? Then we have 5 configurations. One molecule gets all 4 quanta, one molecule gets 3, the other gets 1, 2 molecules get 0, etc., etc. We have 5 configurations. The number of microstates associated with those different microstates are 4, 12, 6, 12, and 1. Alright, why 12 here? You can see we have 3, 1, 0, 0. So these 2 numbers are the same, but other numbers are just different. We have 3 energy quanta and 1 energy quantum, and then 0 and 0. So we need to select the first molecule to receive 3 energy quanta. We have 4 options. Alright, and then we need to select a second molecule to receive 1 energy quantum, and we have 3 options. So for example, the 4 molecules are labeled A, B, C, D. Alright, and we can have A receiving 3 energy quanta, and then we can pick either B or C or D to receive 1. Alright, so 3 options over there, 3 microstates already. Now we can have B receive 3 energy quanta, and then A or C or D receives the remaining 1, 3 options. And then we can have C receive 3 energy quanta, D receive 3 energy quanta, so we have a total of 12. Alright, 12 microstates associated with this configuration alone. But when you have 1, 1, 1, 1, there's only 1 microstate. I mean, that's just one possible way of arranging this. 1, 1, 1, 1. We sum it up, we get 35, but also we can use this equation. M is 4, we have 4 energy quanta. N is 4, we have 4 molecules. So on top we have 7 factorial, on the bottom we have 4 factorial and 3 factorial. Do this calculation, get 35. When 4 energy quanta are shared among 5 molecules, we still have only 5 configurations. They are here. The numbers of microstates are this. We do have more microstates. It's going to be 70, and also we can verify this 70 microstates using the equation. In this case, m is 4, n is 5. We plug in all the numbers, so we get 70. All right, we get 70. Now let's look at something in chemistry. The entropy of the system increases when energy is more dispersed. Entropy is the measure of the dispersal of energy. So Boltzmann proposed that entropy is K sub B, the Boltzmann constant, times the natural logarithm of W. W is the number of microstates. K sub B is the ideal gas constant divided by Avogadro constant. K sub B is 1.38 times 10 to the power of negative 23 joule per Kelvin. And W is the number of ways of distributing energy among the particles, and more specifically among the many different energy levels of those particles. In general, when there are more energy quanta or more molecules, we're going to have more configurations and more microstates. When we have more microstates, we have higher entropy. Boltzmann proposed that the entropy is just the Boltzmann constant K sub B times the natural logarithm of W. W is the number of microstates accessible to the system. That means this system can be in any one of those microstates. The entropy of a system depends on the number of particles and also the total energy of the system. In thermodynamics, we have learned that the entropy is an extensive property. So we do expect to see the entropy of a system is proportional to the number of particles in the system. For example, the entropy of 2 million helium gas atoms is twice the entropy of 1 million helium gas atoms under the same condition, assuming the same pressure, same temperature. The entropy of 2 mole helium gas is twice the entropy of 1 mole helium gas, again under the same conditions. Now here's a numerical example problem 24.2.1. Calculate the entropy of 10,000 coins and the entropy of 2,000 coins, assuming each coin has 2 microstates with equal probabilities, 50-50. 1,000 coins has this many microstates, 2 to the power of 10,000. And then the entropy is Kb times the natural logarithm of W. W is the number of microstates. 2 to the power of 10,000. We plug in the numbers, we get this. This is the entropy of 10,000 coins. What if we have 20,000 coins? Here's the entropy. The entropy of 20,000 coins is twice the entropy of 10,000 coins. Entropy is extensive. Entropy is proportional to the number of coins. In statistical thermodynamics, the configuration associated with the most number of microstates is called the predominant configuration. The Boltzmann entropy calculated using just the number of microstates associated with only the predominant configuration is really close to the exact Boltzmann entropy calculated with all possible microstates. Here's a numerical example. When there are 10,000 particles, each having 2 possible microstates, the 10,000 particle system may have this many microstates in total, 2 to the power of 10,000. The exact Boltzmann entropy is defined to be this. We plug in the numbers, we get the Boltzmann constant times the natural logarithm of 2 to the power of 10,000, which is 6,931 times Boltzmann constant. The predominant configuration, however, involves 5,000 particles in each of the 2 possible microstates. Well, if we're talking about quarters, 5,000 heads, 5,000 tails. But over here, just in more general, we are talking about just 10,000 particles with 1/2 in one of the 2 microstates and 5,000 in the other microstate. So you can imagine, 10,000 electrons, with 5,000 in the up spin state, 5,000 in the downspin state. All right, so more general. The corresponding Boltzmann entropy using only the number of microstates associated with this predominant configuration is this. It's going to be 10,000 factorial over 5,000 factorial over 5,000 factorial. This is the number of microstates associated with this single predominant configuration. We get this number times KB. Compare these two numbers, they're awfully close. So we simply can ignore all other configurations. We just use the predominant configuration, we get the entropy. What's the percent error? Extremely small, because this number divided by this number, you get 0.9993. So even if you just use one configuration, the predominant configuration, and use the number of microstates associated with only that predominant configuration, you can calculate this Boltzmann entropy with only 0.07% error in this case. In thermodynamics, a system often contains much more than 10,000 particles. When that's the case, it's much more accurate to calculate the entropy by just counting the microstates associated with only the predominant configuration. So what if we have like a million particles in two different states, like a million electrons? They can be in the upspin state or downspin state. The predominant configuration has 500,000 in the upspin, 500,000 in the downspin. So over here, this is the total number of microstates. We're going to take the logarithm of it. And 2 to the power of a million, that's the total number of microstates. We take a logarithm here because of this Boltzmann equation. We need to take the logarithm of the microstates. And we compare these two numbers. The first number is 693,140. The bottom number is 693,147. So you can see how close these two numbers are. If you just use the number of microstates associated with the single predominant configuration and ignore all other configurations, you're fine. You'll get 99.999% of the exact entropy. Very, very small error over there. Later, we will prove that the predominant configuration assumes the Boltzmann distribution using the method of Lagrange multipliers. So first, we're going to prove this in section 3, and then in section 4, we'll just count the number of microstates associated with the single predominant configuration and use that to compute the entropy of a system. Chapter 24, Probability and Statistics. Section 24.3, the method of Lagrange multipliers. The method of Lagrange multipliers is often used to optimize a multivariable function with constraints. Here we study a simple example using the method of Lagrange multiplier to optimize our function under a constraint. Let's minimize this function given this constraint. The constraint is this: x plus y plus 2z plus 2u equals 9. We need to rewrite this constraint in this format: x plus y plus 2z plus 2u minus 9 is 0. We first define the Lagrange function, or so-called Lagrangian, L. L is the function to be minimized here, minus this alpha is a parameter, or it's called Lagrange multiplier, times the constraint. This constraint is always 0. X plus y plus 2z plus 2u minus 9 is always 0. So really L is the function to be minimized, minus alpha times 0. To minimize L, we use the typical method. The first derivative of L with respect to x, y, z, and u should be 0. That's what we do here. dl over dx is 2x. From here, minus alpha. From here, it should be 0. dl over dy should be 0. It's 4y, and then minus alpha, it's 0. dl over dz is 8z. From here, and then minus 2 alpha. From here, it should be 0. dl over du should be 0. And these four equations must hold true regardless the value of alpha. So to minimize the Lagrangian L, we have x is 1/2 of alpha, y is 1/2, a quarter of alpha, z is a quarter of alpha. From here, u is 1/2 of alpha. Now, because of this constraint, we know x plus y plus 2z plus 2u should be 9, and then we can plug in the expressions of x, y, z, and u in terms of alpha, and we determine the value of alpha. Alpha has to be 4 to ensure this constraint is true. We then get the values of x, y, z, and u easily because they are expressed in terms of alpha. We just plug in alpha equals 4 here, here, and here, and here, and x, y, z, and u are 2, 1, 1, 2. We plug in the values of x, y, z, and u into this function where c, the minimum value, is 18. Now you may ask, what if we do not have the constraints? Well, it's pretty simple. The minimum value should be just 0. When x, y, z, and u are all 0, this function is minimized with the value of 0. With this constraint, well, the minimum value is 18. So you may also try some other possible values. What if x is 9? All other 3 are just 0. You can plug it in when x is 9. Well, you just plug it in. 9 squared is 81. That's definitely greater than 18. You can try some other combinations. You can say, well, maybe this is 3, and this is 1, and this is 1, and this is 0, stuff like that. You plug it in. You'll get a value greater than 18. Now let's look at another example, problem 24.3.1. Use the method of Lagrange multipliers to minimize another function. And this time we have two constraints. X plus y plus 2z minus 5 must be 0. X minus u minus 1 must be 0. Now we have two constraints. We need two Lagrange multipliers, alpha and beta. So L is defined to be the function to be minimized, and then minus alpha times this constraint. So x plus y plus 2z minus 5 must be 0. X minus u minus 1 must be 0. And I put two Lagrange multipliers in front of this 2. Now I'm going to do dl over dx should be 0, dl over dy should be 0, dl over dz should be 0, dl over du should be 0. And then from this equation, we see x is 1/2 alpha plus 1/2 beta. From this equation, y is a quarter of alpha. From this equation, z is 1/2 of alpha. From this equation, we have u is negative beta over 4. So again, you just need to know just simple derivative calculus operations, and then you can get this. You express x, y, z, and u in terms of alpha and beta. And remember, we have two constraints, so we plug in the expressions of x, y, z, and u into these two constraints. We have this, two constraints. Alright, so this is x, y, and this is this is x, this is y, this is 2 times z equals 5, and x minus u is 1, so this is x minus u, which is plus a quarter of beta, is equal to 1. So look, we have two linear equations that contain only two variables, alpha and beta. We can solve them. So alpha has to be 52 over 17, beta has to be negative 12 over 17 to satisfy both constraints. Now we have the values of alpha and beta. We plug them into these expressions of x, y, z, and u. We get the values of x, y, z, and u. And then we can determine the minimum value of this function under these two constraints right here. Of course, you can try some other combinations. You will get a value greater than this. In sum, to minimize or maximize a function under a constraint, g is 0, we need to set a Lagrangian. L is the function to be optimized minus a Lagrange multiplier alpha times the constraint g. G is always 0, therefore L is equal to f. Then we obtain four equations by setting dl over dx is 0, dl over dy is 0, dl over dz is 0, dl over du is 0. Using these four equations and also using this, we can solve for alpha, x, y, z, and u. Because we have four equations here, we have another equation here, we have 5 equations in total, and we have 5 variables. So we can solve for the values of alpha, x, y, z, and u. And usually we just express x, y, z, and u in terms of alpha and then plug into the constraint over here and solve for the value of alpha first. And then we get the values of x, y, z, and u. So anyway, this is pretty simple. We can just minimize or maximize a function under this kind of constraint. What if there are two constraints? Alright, two constraints, g is 0, h is 0. And then we simply need another Lagrange multiplier. Let's call it beta. L, the Lagrangian, is now the function to be optimized. Minus alpha times the first constraint minus beta times the second constraint. And then we solve this four equations. dl over dx is 0, dl over dy is 0, dl over dz is 0, dl over du is 0. This is to express x, y, z, and u in terms of alpha and beta. And we have two constraints. Remember, x, y, z, and u can be expressed in terms of alpha and beta. Now we have these two equations. We have two equations that contain only two variables, alpha and beta. We can solve those. We get the values of alpha and beta. And then because x, y, z, and u are expressed in terms of alpha and beta, we can then get the values of x, y, and z, and u to minimize or maximize this function f. So this is in general how we use the method of Lagrange multipliers to optimize a function under constraints. In physical chemistry, we use the method of Lagrange multipliers to find the most probable configuration. That means the predominant configuration with the most number of microstates of a thermodynamic system under the constant Ne constraints. So what if we have an isolated system, we have a bunch of molecules with a constant energy, and then we can find the predominant configuration. We can calculate the associated number of microstates, and then we use that to compute entropy using Boltzmann's equation. Entropy equals the Boltzmann constant times the natural logarithm of the number of microstates. Again, we just use the number of microstates associated with the most probable or predominant configuration. Here is the total number of particles in the system, and E is the total energy of the system. We're assuming we have many energy levels, epsilon 1, epsilon 2, epsilon 3, etc. And we're going to assume in epsilon 1 we have A1 particles. In energy level epsilon 2 we have A2 particles. In energy level epsilon I we have AI particles. Therefore, N is equal to the sum of AI, and E is equal to the sum of AI times epsilon I. Chapter 24, Probability and Statistics, Section 24.4, Boltzmann distribution. The mathematical expression of the Boltzmann distribution is this: AI over AJ is equal to E to the power of negative energy difference over kBt. A sub I is the number of particles that occupy the energy level I. A sub j is the number of particles in energy level j. So the ratio between AI and AJ is the ratio between these two exponential functions, e to the power of negative epsilon I slash kBt over e to the power of negative epsilon j over kBt, the ratio between these two. So essentially, the number of particles is proportional to the exponential function of negative energy over kBt. The Boltzmann distribution is the most probable distribution when the number of particles n and the total energy E of the system are held constant. The proof is as follows. If n particles occupy various energy levels, the total number of microstates W is this. W is n factorial over A1 factorial, A2 factorial, A3 factorial, etc. W may be viewed as the number of permutations of n particles, that's n factorial, but among which the permutations of A1 particles are indistinguishable. So if we have, for example, 5 particles in energy level 1, Well, that's just one arrangement. So we need to have this n factorial over a1 factorial. So whether you have A, B, C, D, E in energy level 1 versus B, C, D, A in energy level 1, it's the same thing. We need to look at every single energy level. Therefore, the expression is this. It's n1 factorial over n2 factorial, n1 factorial, n factorial over a1 factorial, a2 factorial, etc. This denotes product. So this is just the product of all those factorials. Now, when the number of particles and the total energy E are held constant to maximize W, within these two constraints, we can choose to maximize the natural logarithm of W for convenience. The natural logarithm of W is the natural logarithm of n factorial over, on the bottom, the product of all those factorials, and therefore it's just the logarithm of n factorial minus the sum of the logarithm of ai factorial. Again, we have two constraints. The first constraint is the total number of particles must be n. The second constraint is this: the total energy must be E. N is a constant, E is a constant. Now we define the Lagrangian L with these two constraints. The Lagrangian L is defined to be the natural logarithm of W, the number of microstates of the most predominant configuration, minus alpha times the first constraint over here. This is 0 always, minus beta times this constraint, always it's 0. Alpha and beta are called Lagrange multipliers. Now let's optimize this Lagrangian. How do we do this? We just need to take the first derivative of this Lagrangian with respect to a1, a2, a3, a4, etc. Again, this Lagrangian is ln n factorial minus the sigma of ln ai factorial, because w is n factorial, divided by the product of a1 factorial, a2 factorial, etc. So we have this from ln w over here. And then we copy the two constraints here and here, multiply by this Lagrange multipliers, alpha and beta, and we set dl over da1 is 0, dl over da2 is 0, etc. So first, dl over da1 is 0. So over here we have dl on top, da1 on the bottom. How do we evaluate this? Well, first we need to remember n is a constant. The total number of particles is a constant. The total energy is a constant. So when you see uppercase n, when you see uppercase n here, and when you see e here, we can chop them. They do not depend on da1. So we have this simplified expression over here. So this goes in here, this part goes in here, and it's chopped, and this part goes in here. Alright, and also because N2 is independent of A1, A3 is independent of A1, A4 is independent of A1, etc., etc. So when we look at this sum, only one term in this sum depends on A1. That is this. Only one term in this sum depends on A1. Only one term in this sum, a series of terms. Only A1, epsilon 1 depends on A1. So we further simplify the expression to here. Now it's really simple. I have only 1, 2, 3. Only 3 terms. By maximizing the Lagrangian, we get this equation. We can just evaluate this derivative, and this derivative. It's a little tricky to evaluate the derivative of the logarithm of a1 factorial. We need to use Stirling's approximation. Well, Stirling's approximation is this: the natural logarithm of x factorial is approximately x times L1x minus x when x is large. So we can just simply use this approximation. We say ln a1 factorial is a1 times ln a1 minus a1 over here. And then we can just evaluate those integrals easily. Over here we use the product rule. It's ln a1 plus a1 times 1 over a1, which is 1, and then minus 1 over here. And then This is just simply alpha, this term, okay? Negative alpha times A1 over dA1 is just negative alpha. Over here it's just negative beta times epsilon 1. We get this expression. 1 and negative 1 cancel, so we have ln A1 is just negative alpha minus beta epsilon 1. It's pretty simple. See, we got a nice equation for A1. A1 is expressed as in terms of alpha and beta, and it does depend on epsilon 1. You can see that we can derive similar equations for A2, A3, A4. Now we prove Stirling's approximation. This is true when x is large. So first, ln x factorial is the sum of ln1, ln2, ln3, ln4, ln5, all the way to ln x. And the sum of ln x is roughly the integral of ln n dn. So look at here. The integral of ln dn is the area below the red curve. The red curve is ln x, alright? And what about those bars? Those bars are ln1, ln2, ln3, ln4, ln5. Alright, the height of the bars is ln0, ln1, ln2, ln3, ln5, ln4, ln5, etc. So if you look at the area of the bars, it's ln0 times 1, ln1 times 1, ln2 times 1. So if you sum up all those bars, it's going to be the sum of ln x over here. Alright, and by just looking at this, the integral of the red curve is approximately the sum of the areas of all the bars, right? If you sum up all the bars, approximately this sum is going to be roughly the integral value, which is the area under this red curve. So we have this approximation, and we just need to know what's the integral of ln n. It's n times ln minus n. We plug in all those values, we get this. And then finally we make a little bit approximation, we get this. ln x factorial is roughly x times ln x minus x. We can verify this with some numerical examples. Let's say x is 10,000. The logarithm of 10,000 factorial is 82,109. And then we look at the approximation, 10,000 times ln 10,000 minus 10,000. Well, it's 82,103, so you can see this too. Well, differ by only roughly 5 out of 80,000. It's a small percentage error. It's a very small percentage error. So that's why we can use the Stirling approximation here. The logarithm of a1 factorial is roughly a1 times ln a1 minus a1. So that we can evaluate this derivative and we get this nice relationship. You know, a1 can be expressed in terms of alpha and beta, and later we'll see we can express a2 in terms of alpha and beta similarly. So again, keeping this Lagrangian, we maximize ln w with two constraints here and here, multiplied by the Lagrangian multipliers alpha and beta, and we have different equations to evaluate. dl over dA1 is 0, dl over dA2 is 0, dl over dA3 is 0, etc. When we use Stirling's approximation, we can simplify this part, and then we can evaluate dl over dA1. This should be 0, and we got this equation. The logarithm of a1 should be negative alpha minus beta times epsilon 1. a1 is expressed in terms of alpha and beta. Similarly, a2 can be expressed in terms of alpha and beta. Just exactly same derivation. Instead of doing the derivation for energy level 1, we just do the derivation for energy level 2, we get this equation. And similarly, we get other equations for energy level I, energy level J. So you can see the expression is this for AI, the expression for this, you know, for energy level J. Now, we take the ratio between AI and AJ. AI over AJ is e to the power of negative alpha times e to the power of negative beta epsilon I over a similar expression with level J here, and e to the power of negative alpha, e to the power of negative alpha cancel. We get this. What is this? Actually, this is Boltzmann distribution. Now, what is beta? Experimentally, we can measure the populations in various energy levels. for a constant NE system and obtain the value of beta. So for example, if you know this energy level, you know this energy level, and if I know there are 200 particles here in this energy level, 500 particles in this energy level, we plug in all the numbers, and then we solve for beta. It turns out beta is 1 over kBt, and the kB is Boltzmann's constant, T is the temperature. The value of kB is exact. kB is actually the ideal gas constant over Avogadro constant. The value of kB is 1.380,649 times 10 to the power of negative 23 joule per Kelvin. I think this is UPAC definition or NIST definition, I forgot, but this is the exact value. Again, R is the gas constant, N sub A is Avogadro constant. So you can actually get the value of R by multiplying this with Avogadro constant, I think, which is 6.02214076 times 10 to the power of 23. So, and then you get R. The mathematical expression of the Boltzmann distribution is this. Again, AI over AJ is the ratio between these two exponential functions, e to the power of negative energy over kBt. This is the energy of the ith energy level, this is the energy of the jth energy level, and then we can combine this two. It's e to the power of negative energy difference over kBt. The higher the energy, the smaller the occupation number. Again, A sub I is the number of particles that occupy the energy level I. So A sub I is the population or the occupation number of energy level I. Here, let's study a numerical example. Consider a collection of 900,000 particles that occupy 3 energy levels, 0, epsilon, 2 epsilon. What if the total energy is 400,000 epsilon? And then let's compute the maximum number of microstates associated with the single predominant configuration. We have two constraints. N1 plus N2 plus N3 has to be 900,000. This is the total number of particles. Now let's look at the energy. Well, N1 particles, they have 0 energy. N2 particles each has epsilon. N3 particles each has 2 epsilon. So we have another constraint over here. And now let's just do it. You know, N1 is simply 900,000 minus N2 minus N3. N2 is simply 400,000 minus 2 times N3, etc. We get these two equations. And we can then express N1 in terms of N3, and then W should be N factorial on top. And then N1 factorial, N2 factorial, N3 factorials on the bottom. And now we have the expression of LNW. W is the number of microstates. Alright, this is the expression of LNW in terms of only one variable, N3. How do we maximize this? Well, the first derivative of LNW should be 0. So we take the first derivative. We do need to use Stirling's approximation. If we take the first derivative of ln x factorial, we expand this into x ln x minus x. Well, this is Stirling approximation from the logarithm of x factorial to x times ln x minus x. And the derivative of x times ln x is very simple. It's ln x plus x times 1 over x, and then minus 1 over here, we get ln x. So the derivative of the logarithm of x factorial is simply ln x. And then we can just simplify this expression. We get this minus 2 times this plus this. It's just 0. And it's a very simple equation. It's simplified to a quadratic equation that we can solve. All right. So mostly it's just this term divided by this squared multiplied by this should be 1. Alright, that's just typical logarithm operation. How do we solve this? Well, it's just a quadratic equation. You can solve it by yourself. I used the Wolfram alpha. I got the values for N3. It can be this, it can be this. It cannot be this, because if you get this, then the value of N2 is going to be negative. That's unphysical. You cannot have a negative number of particles in energy level 2. or any other energy levels. You cannot have a negative number of particles. So N3 has to be 87,000. And then N2 is this, 225,000-ish, and N1 is 587,000-ish. Now we calculate the ratios between those occupation numbers or populations. N2 over N1 is 0.385. N3 over N2 is also 0.385. These two ratios are exactly the same. Is this a coincidence? No, it's not. Well, this is an example of the Boltzmann distribution when two energy spacings are the same. When you have two energy spacings and the two ratios are the same. The temperature of the system is proportional to epsilon. The proof is very simple. N2 over N1, N3 over N1 is simply e to the power of energy spacing or energy difference over kBT. So between the three energy levels, 0 epsilon and 2 epsilon, well, the energy spacing is just epsilon. So we have this equation, and this equation, e to the power of negative energy difference over kBT, should be the ratio 0.385, and then we solve this equation. We get temperature is equal to epsilon over 0.9545 kb. Alright, so if you know the value of this epsilon, you can compute the temperature. If you are given temperature, you can compute epsilon. The total number of microstates of this predominant configuration is this. We have 900,000 particles in total, so that's 900,000 factorial on top. We have three occupation numbers in the first, second, third energy levels. 0 epsilon, 1 epsilon, 2 epsilons, and then we can compute W. W is huge. W is 10 to the power of 332,855. It's a huge number over here. This is W. That's the number of microstates associated with the predominant configuration with two constraints. The total number of particles is 900,000. The total amount of energy is 400,000 epsilon. Using the number of microstates, assuming the Boltzmann distribution among the three energy levels, we have the Boltzmann entropy. The Boltzmann entropy is just K sub B times the logarithm of W. So over here, we use the number of microstates associated with only one configuration, the predominant configuration. With this many microstates, we take the logarithm of W, we get this many kb. Of course, you can plug in the value of kb to get the value of entropy, but let's not do that. Let's just use kb as the unit of entropy. It's just more convenient. The total number of microstates of all possible distributions. What if we assign 400,000 quanta of energy to 900,000 particles? What's the exact number of microstates? We're going to use this formula. We learned this formula before. We will prove this formula later. The total number of microstates is this: the number of energy quanta plus the number of particles minus 1 factorial. On the bottom, the number of energy quanta factorial, and the number of particles minus 1 factorial. So we can do this. We get 10 to the power of 348,000. Using the total number of all microstates associated with all configurations, we get this entropy. Now let's compare this entropy from the single predominant configuration. This is the entropy from all configurations. What's the difference? Well, this divided by this, we get 95.5%. It's not too bad. It's not too bad. So for this example problem, if we use just one single configuration, the most probable configuration, the predominant configuration, we can recover 95.5% of the total entropy. There is 4.5% error, and this error is mainly due to the particles being restricted to have only 2 epsilon or 1 epsilon or 0 epsilon. So what if we allow all those particles to occupy even 3 epsilon, 4 epsilon, even 400,000 epsilon energy level, and then calculate the entropy for the most probable configuration or predominant configuration, And then we will be able to get a value extremely close to the exact entropy. Now let's do it. Let's use the method of Lagrange multipliers to study this similar numerical example. But this time we will allow those particles to occupy higher energy levels. We will allow the particles to be in an energy level of 3 epsilon, 4 epsilon, 5 epsilon, or even 400,000 epsilon. So you can indeed have one particle in this energy level, and all other particles with just zero energy. Now again, we have constraints here. The total energy is 400,000 epsilon, and the total number of particles is 900,000. We define a Lagrange here. L is Ln(w) minus alpha times the first constraint for the number of particles minus beta times the second constraint regarding the total energy. The number of microstates is this, n factorial over a0 factorial, a1 factorial, a2 factorial, a3 factorial. So over here, a0 is energy level with 0 energy, a1 is the energy level with 1 epsilon, 2 epsilon, 3 epsilon, all the way up. Actually, it's not infinity here. It should be 400,000. I put infinity here. It's not wrong because simply in this energy level of 1 billion epsilon, the occupation number is just 0. 0 factorial is 1 anyway. It's not going to affect the value of this. So this equation is also correct. Now A sub I is the number of particles that occupy energy level I. A sub I is also called the occupation number. A sub I is also called the population in energy level I. Now the Lagrange is this. Alright, we plug in the number n is equal to 900,000 and E is 400,000 epsilon. So we need to set dl over dA0 is 0, dl over dA1 is 0, dl over dA2 is 0, etc., etc. Alright, we're going to do all this. Alright. And then we have this equation. Remember, we can simply use Stern's approximation. Ln AI factorial is AI times Ln AI minus AI. Alright, so we can also, because A2 does not depend on A1, A3 does not depend on A1, A4 does not depend on A1. So when we are doing this, this is the first derivative of a sum. We can just look at one of the many terms, just the A1 terms. It's going to be here. All right, this is going to be here. We have this equation, and then we use Stern approximation. I think this derivative is just the logarithm of AI. This is easy. We have the first derivative of a sum, and among all those terms, there's only AI term that depends on AI. Also over here, among all those terms in the sum, only AI epsilon I depends on AI. So the derivative is epsilon I. So those are just mathematical kind of just operations. Let's just work on it. Let's do dl over dAI. Again, out of just the many terms in a sum, only one term depends on AI. So we have this depends on AI, this depends on AI, this depends on AI. And we use Stern's approximation, which is this. The logarithm of x factorial is roughly x times ln x minus x. So we can evaluate this dl over dAI. This part is pretty simple. It's going to be just ln AI with a negative sign in the front and the minus alpha minus beta epsilon I. So we got this equation. And in general, A sub I is e to the power of negative alpha times e to the power of negative beta times epsilon I. The total number of particles is 900,000. So the sum of all those occupation numbers should be 900,000. This looks really complicated. Alright, the sum of e to the power of negative alpha, e to the power of negative beta epsilon I is 900,000. To simplify this, we have some tricks. We will set Q to be the sum of e to the power of negative beta epsilon I. So we do this. Alright, so when we do this, honestly, this Q has physical meaning in physical chemistry. It's called partition function, but it's going to be introduced in the last chapter. So for now, we'll just say, well, Q is the sum of those exponential functions. Alright, e to the power of negative beta epsilon I. So I is from 0 to infinity. Alright, so we have the expression of q here. And once we have the expression of q here, you can see, given this equation, you can see e to the power of negative alpha. Alright, this term does not contain I because it's just alpha, the Lagrange multiplier. I can take this out of the sum. So this sum is e to the power of negative alpha multiplied by the sum of e to the power of negative beta epsilon I, which is just q. Alright, remember, e to the power of negative alpha, we take it out. Alright, e to the power of negative alpha, we take it out. It times this sum is n. And that sum is just defined to be the q, partition function. Alright, so e to the power of negative alpha is n over q. Again, q is the so-called partition function in statistical thermodynamics. Now, a sub I is simply just n over q times e to the power of negative beta epsilon I. So how do we get this? Well, over here, you can see, a sub I is e to the power of negative alpha times e to the power of negative beta epsilon I, and e to the power of negative alpha is what? It's n over q. So this is n over q, this is n over q, this part is n over q. Alright, so a sub I is n over q times its exponential function over here. And we can evaluate this q. Q is the sum of many exponential functions, so we can expand this sum. It's 1 plus e to the power of negative beta epsilon, e to the power of negative 2 beta epsilon, because we have 2 epsilon energy. In that energy level, e to the power of negative 3 beta epsilon, etc. Now, how do we evaluate q? Well, both sides can multiply by this. Same thing, alright? So we have q multiplied by this, and all this multiplied by this. So on the left-hand side, it's q multiplied by this exponential function. On the right-hand side, it's this exponential function multiplied by a sum, which is 1 plus e to the power of negative beta epsilon plus e to the power of negative 2 beta epsilon, etc. So let's do this multiplication. We get this. Let's do this multiplication. We get e to the power of negative 2 beta epsilon, and then e to the power of negative 3 beta epsilon. Now let's examine this the sum here. Look at this sum. This sum is mostly just this sum, except 1. So this whole thing is simply this q minus 1. Alright, now this is a trick. E to the power of negative beta epsilon times q is simply q minus 1. Alright, so now we have this simple equation. E to the power of negative beta epsilon times q is just q minus 1. So q is just 1 over 1 minus e to the power of negative beta epsilon. So we get this expression of q, and before we have a sub I is n over q times e to the power of negative beta epsilon I, and then we can replace this q with 1 over 1 minus epsilon e to the power of beta epsilon, and then a sub I. The occupation number of energy level I is the total number of particles times e minus e to the power of negative beta epsilon, and then times e to the power of negative beta epsilon I. Epsilon I is the energy of the I's energy level, and over here this is the reciprocal of q, and then we get a nice equation for the occupation number. Again, q is defined to be the sum of e to the power of negative beta epsilon I. This is by definition. Q is called the partition function. dq over d beta, we're going to evaluate this, is the derivative of the sum. The derivative of the sum is the sum of the derivative. That's just calculus. And now let's take this derivative. It's simple. It's the exponential function. It's itself multiplied by epsilon I with a negative sign, because you need to use the chain rule to take the derivative of negative beta epsilon I with respect to beta as well. It's negative epsilon I. And then also you copy the exponential function over here. Alright? Why do we want to do this? Well, this is related to the energy of the system. Let's see. The total energy of all these particles, well, we know it's 400,000 epsilon. Now let's do some derivation. The sum of ai epsilon I is the total energy, and we know a sub I is n over q times this exponential function e to the power of negative beta epsilon I. And then we have epsilon I over here, right? Look, n does not depend on I. Q does not depend on I. So I take this N over Q out of the sum. We have N over Q times the sum of e to the power of negative beta epsilon I epsilon I. I think we saw this before, right here. Okay, this is this. Alright, just with one negative sign here. So the total energy should be N over Q times this guy, dq over d beta, with a negative sign. So the total energy should be 900,000, which is the total number of particles n, over q, times negative dq over d beta, because dq over d beta is negative this sum. Alright, and this should be 400,000 epsilon. That's the total energy. And then we have this expression, dq over q over d beta is negative 4 over 9 epsilon. So we got this equation over here. Alright, that's kind of interesting. We got this equation. We got this equation, and we've got the expression of q. We derived this in the previous page. And now what we need to do is we just need to plug in the expression of q in here. It's going to be dq over d beta. We're going to evaluate that, and we have 1 over q. 1 over q is simply this denominator, so we copy that here, and we do dq over d beta. We're going to use chain rule. We're going to get negative 1 over this thing squared, and then we'll have to take the derivative of whatever in this pair of parentheses, which is epsilon times e to the power of negative beta epsilon. Alright, so this whole thing is negative 4 over 9 epsilon. And now we need to clean it up. Alright, we need to clean it up. It's pretty easy, because you see this expression here, and you see the same thing squared. So we'll just keep one of this, alright, on the bottom. On top, we have e to the power of negative beta epsilon, right? Negative sign cancel. Epsilon and epsilon cancel, so we get this expression. Once we have this expression, we can easily get the value of e to the power of negative beta epsilon. It's 4 over 13. You have 4 over 13 on top. You have 9 over 13 on the bottom. Alright, 4 over 13 divided by 9 over 13. You get 4 over 9. So really nice. We got this. See, if you know the value of beta, we determine epsilon. If you know epsilon, we can determine beta. Get back to this. A sub I is the occupation number. We can express A sub I as N over Q times e to the power of negative beta epsilon I, and also Q is the reciprocal of this. Q is the reciprocal of 1 minus e to the power of negative beta epsilon. And we even determine the value of e to the power of negative beta epsilon, which is 4 over 13 from the previous page. And beta has a physical meaning. The reciprocal of beta is kBt. And the kBt is the reciprocal of beta. And we know this negative beta epsilon is the logarithm of 4 over 13. So over here, and then we can see kBt is proportional to epsilon. In this system, kBt is 0.848 epsilon. Alright, again, if you know epsilon, you determine temperature. If you know temperature, you can determine epsilon. Now let's look at the expression of A sub I, and we can compute the occupation numbers. A sub I is this. Again, it's just this. Over here, e to the power of negative beta epsilon I is simply this, because epsilon I is simply I times epsilon, right? When I is 0, we have 0 energy. When I is 1, we have 1 epsilon. When I is 2, in energy level 2, we have 2 epsilon. In energy level 3, we have 3 epsilon. So we got this. And e to the power of negative beta epsilon is 4 over 13. So we got this expression. Alright, so this is the expression of A sub I, and we know n is 900,000. We just need to plug in I equals 0 to get A0. When I is 1, we get A1. When I is 2, we get A2. When I is 3, we get A3. So we got all those numbers. Those are the number of particles in energy levels 0, 1, 2, 3, 4, 5, 6. And you can keep computing this. So I did this in an Excel spreadsheet. So when energy level 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, you can see the occupation numbers decrease. And that's just the Boltzmann distribution. You know, when you have higher energy, you have a lower occupation number. Alright, and the Boltzmann distribution is an exponential function. Given those occupation numbers, now we can use this equation to calculate the number of microstates associated with just one single predominant configuration. So this configuration, all right, we have in this configuration, we have maximized the number of microstates. And in this predominant configuration, we have this many particles in this energy level 0, this many particles in energy level 1, etc. All right, now let's look at the Boltzmann entropy. It's the logarithm of this times kb. All right, so we'll just evaluate this. Unfortunately, there are so many different energy levels. So over here, we compute energy level 6 over here in the graph. We computed energy level 6, 7, 8, 9, 10 as well, from 0 to 10. And okay, you can see over here the occupation number is pretty small already. So you can plug in I equals 10 over here, and A sub 10 is pretty small. And we continued to calculate it, A sub 11, 12, 13, 14, 15, and 16. All right, and then we will include the 16 lowest energy levels in this calculation. It's just impractical to include all those energy levels. We'll just look at the top 16. So we're going to estimate the entropy this way, all right? And the entropy is the logarithm of 900,000 factorial, and then minus ln over here, this A0 factorial, A1 factorial, A2 factorial, A3 factorial. We just keep going. We all the way go to A16 factorial. And we get this much kb. All right, it's 802,440 kb. Well, you can try to include energy level number 17, 18, 19, 20. You will get pretty much the same value here. Yeah, look, this is the entropy we calculated using the number of microstates associated with only one configuration, the most probable configuration or the predominant configuration. We get this number. We computed the exact entropy before, which is 802,407. All right, so by using this formula to get the total number of microstates, all right? So this is how we get the exact number of microstates and the exact entropy for the system with 900,000 particles and 400,000 energy quanta. Now compare these two values. This is the exact entropy, and this is the entropy from only one predominant configuration. What's the difference? Very small difference. They differ by only 0.001%. So it's really good approximation here. So later you'll see. In statistical thermodynamics, we will only look at one configuration, the most probable configuration, the predominant configuration. We will count the number of microstates for that one configuration and use that to compute the entropy of a thermodynamic system. And that entropy is awfully close to the exact entropy, with a percent error actually lower than this. Because usually we have a thermodynamic system that contains more than 900,000 particles. The more particles we have, the better, the more accurate this approximation will become. Right, again, we made actually several approximations. Number one approximation, we assumed that only the predominant configuration should be considered. I didn't even look at any other configurations. Even the second most predominant configuration is not considered. All right, we only looked at one single predominant configuration. And we make another approximation here. We looked at only the top 16 energy levels. I didn't even include energy level 17 epsilon, 18 epsilon, 19 epsilon, etc. But if you do, you still will get a number really close to this. All right, really close to this. Number 3, I think we used the Stirling approximation in our derivation. We assume the natural logarithm of x factorial is equal to x times ln(x) minus x. So we made 3 different approximations, but in the end, we still computed the entropy of the system really accurately within a 0.001% error. So that's very impressive. Chapter 25, Statistical Thermodynamics, Section 25.1, Ensembles and Partition Functions. An ensemble is a collection of replicas of a system. Each replica is a mental copy of the same system. The average properties of a very large number of replicas of the same system in an ensemble are equal to the time-averaged property of such a system. There are various types of ensembles. So first, let's look at the NVE, microcanonical ensemble. It's a collection of replicas of a system, and all those replicas have a fixed number of particles, volume, and energy. The NVE ensemble depicts an isolated system. NVT, canonical ensembles. There are collections of replicas of a system all having a fixed number of particles, volume, and now temperature. The NVT ensemble depicts a closed system immersed in an isothermal bath with a constant temperature. A mu-VT ground canonical ensemble is a collection of replicas of a system all having a constant chemical potential, volume, and temperature. The mu-VT ensemble depicts an open system at a constant temperature, constant volume, that allows for matter exchange. A MPT Gibbs ensemble is a collection of replicas of a system all having a fixed number of particles, pressure, and temperature. The MPT ensemble depicts a closed system under constant pressure and temperature. Its volume may change. A NPH enthalpy ensemble is a collection of replicas of system, and all those replicas have a fixed number of particles, pressure, and enthalpy. The NPH ensemble depicts a closed system under constant pressure and enthalpy condition. Since we have constant pressure condition, Q is equal to delta H. And since H is constant, Q is equal to delta H, and Q is 0. An ensemble is a collection of replicas of a system, and those replicas are the mental copies of the same system. The NVE ensemble is a collection of replicas of a system all having a fixed number of particles, volume, and energy. The NVE ensemble is also called microcanonical ensemble. The NVE microcanonical ensemble represents an isolated system in which the energy is constant. Specifically, the internal energy is constant. Its entropy is maximized at equilibrium. Because we have this equation, du is TdS minus PdV plus the sum of mu I dNi. This equation comes from the definition of chemical potential mu. Now let's look at this equation. We have constant energy, and specifically constant internal energy. du is 0, dV is 0 because it's constant volume, and dNi is 0 because we have fixed number of particles for each type. So when we see this, that means the number of particles of each kind is constant. And then we have 0 equals TdS minus 0 plus 0, therefore ds is 0. That means, well, entropy is maximized at equilibrium in an isolated system, and that does make sense. Over here, this is just a simple diagram for a microcanonical MVE ensemble over here with a perfect insulation. This shaded area represents a really good insulation, and we have a constant volume, and there's no work, no heat, the energy is constant. Also, we have a constant number of particles inside of each kind. This is again the MVE microcanonical ensemble. Now let's look at a different ensemble. A canonical ensemble is a collection of replicas of a system or having a fixed number of particles, volume, and temperature. The MVT canonical ensemble depicts a closed system. That means there's no matter exchange. It's immersed in an infinitely large thermal bath with a constant temperature T. Alright, so this diagram is a canonical MVT ensemble. Energy exchange is possible, so we can have heat flows in and out. Therefore, there is some energy oscillation in this kind of closed system. However, the number of particles, volume, and temperature are constant. In a canonical ensemble, Helmholtz energy is minimized at equilibrium because we have this equation for dA. dA is negative SdT minus PdV plus the sum of mu I dNi. This comes from the definition of mu. Because temperature is held constant, volume is constant, N sub I is constant, so dA must be 0. In this case, A must be minimized at equilibrium. Now let's look at the mu VT ground canonical ensemble. It's a collection of replicas of a system or having fixed temperature, volume, and chemical potential. So the mu VT ground canonical ensemble is an open system like this. There's matter exchange, there's energy exchange, but the temperature is constant. So you can imagine this is also immersed in a infinitely large thermal bath at a constant temperature, and also the volume is constant because we can simply just study all the chemicals inside this flask, and that means constant volume. However, there's matter exchange. Because dA is negative SdT minus PdV plus the sum mu I dNi, we can see temperature is constant, volume is constant, so dA is the sum of mu I dNi. Also, this constant chemical potential means for every single species mu is constant, and therefore this mu sub I is constant. We can put this mu I inside the differential. dA is simply the sum of the exact differential of Ni mu I. If you integrate both sides, you can see A is simply the sum of Ni mu I plus a constant. Now let's look at the MPT Gibbs ensemble. It's a collection of replicas of a system or having a fixed number of particles N. They have constant pressure P. They have the same temperature T. In this case, Gibbs energy is minimized because dG is negative SdT plus VdP plus the sum of mu I dNi. Again, this equation comes from the definition of mu. And now N is constant. Over here, this sum is 0. P is constant. VdP is 0. T is constant. Negative SdT is 0. Therefore, dG is 0. In MPT Gibbs ensemble, the Gibbs energy is minimized. Therefore, dG is 0. Most chemical reactions in a lab have a constant TP condition. The chemical reactions in an industrial process often also have constant TP condition. Constant T just for consistency, constant pressure for safety. You'd rather have a constant pressure than constant volume. When you have constant volume, well, gas pressure may accumulate inside this constant volume, which may cause explosion. So the MPT Gibbs ensemble depicts this kind of reactions on a constant temperature and pressure condition, and at equilibrium G is minimized. Over here we have Gibbs ensemble, or you can say it's MPT ensemble. We have constant N, constant P, and constant T. You can see there's a piston here now with a constant weight. So the pressure is going to be a constant, the number of particles is a constant, temperature is a constant. Just imagine we put this in a water bath or oil bath with a constant temperature. Finally, let's look at the MPH, enthalpy ensemble. It's a collection of replicas of a system, all having a fixed number of M, P, and H. Because we have constant pressure, that means the heat is isobaric heat, Q sub P. And in thermodynamics, we learned Q sub P is equal to delta H. Over here in this ensemble, H is held constant, so Q sub P is 0. There's no heat flow. In this case, entropy is maximized, because dH is TdS plus VdP plus the sum of mu I dU I, and N is constant. This sum of mu I dU I is 0, P is constant, VdP is 0, and H is constant, dH is 0, so ds must be 0. Entropy must be maximized. We can look at this diagram over here. This is a constant MPH ensemble, and you can see the pressure is constant. We have a piston here. The piston may move, the volume may change, but the pressure is constant. We do have an insulation over here. That is to ensure this Q sub P is just 0, therefore delta H is 0. So by having this really good insulation layer, delta H is 0. And in this case, the entropy of the system must be maximized. At the end, we have an equilibrium, and ds is 0. So we have briefly introduced 5 different statistical ensembles: microcanonical MVE ensemble, canonical MVT ensemble, ground canonical MuVT ensemble, Gibbs MPT ensemble, and this is enthalpy constant MPH ensemble. So in this chapter, we will only focus on 2 ensembles: the MVE microcanonical ensemble and the MVT canonical ensemble. An ensemble is a collection of replicas or many copies of a system. In a canonical ensemble, all replicas have the same number of particles, they have the same volume, same temperature, but each replica may have a different energy. The number of replicas with energy E is proportional to this, e to the power negative E over kBT. This is the so-called Boltzmann distribution. We have learned before the Boltzmann distribution is associated with the most number of microstates, and this is the predominant configuration. The number of replicas with energy E is also proportional to the number of microstates such a system have. These 2 proportionalities result in most replicas having an energy very close to the average energy of all replicas. So if you look at this function, if we have higher energy, alright, this exponential function is smaller. But when you have a higher energy, well, the number of microstates of such a system with higher energy is larger. So these 2 mostly cancel. So in the end, we will see, well, the replicas with the energy that is really close to the average energy of all replicas has the most population. We will then look at one specific example. Let's examine one MVT ensemble that consists of only 25 particles. So all replicas contain 25 particles. Alright, and they have the constant volume and temperature condition. At the same temperature, all replicas in the MVT ensemble may have different energies. So that means energy oscillation is possible, but most replicas have energy very, very close to the average energy. We'll use an Excel sheet to calculate the relative population. That means the probability weighted, or simpler weight of the replicas versus their energy. For convenience, the energy of every replica is an integer multiple of epsilon, where epsilon is just kBt. So we'll just use this condition to simplify the calculation. When we have m energy quanta shared among m particles, there are this many microstates. We learned this from the chapter on probability and statistics. It's m plus n minus 1 factorial over m factorial over n minus 1 factorial. We'll prove this equation in this section. The probability of finding a replica with m energy quanta is proportional to this. The number of microstates, if you have this many energy, if you have this much energy, m times epsilon. And this is Boltzmann distribution, e to the power of negative m epsilon over kBt. So we're going to find this probability, all right? The product of the number of microstates and the Boltzmann distribution function are combined in here. And this is to allow us to estimate, the population of the replicas with, for example, 0 epsilon energy, 1 epsilon energy, 2 epsilon energy, 3 epsilon energy, etc. Now let's prove this equation. When m energy quanta are shared among m particles, there are this many microstates. There are m plus n minus 1 factorial over m factorial over n minus 1 factorial microstates. We'll prove this equation. We're going to just use a diagram here. We will illustrate this situation. M energy quanta being shared among m particles with sticks and circles. Each energy quantum is a stick. Each particle is a circle. Alright, now I'm drawing something like this. We have 8 circles. 1, 2, 3, 4, 5, 6, 7, 8. 8 circles. We have 11 sticks. Alright, so when I draw this, I'm trying to use this diagram to depict a situation in which 2 energy quanta are given to this molecule. 1 energy quantum given to this molecule. 2 energy quanta given to this molecule. 1 given to this molecule. 1 given to this molecule. 1 given to this molecule. 0 energy quanta given to this molecule. And finally 3 energy quanta given to this molecule. Alright, this is just a diagram of the distribution of the sticks to the circles. All the sticks are given to the immediate neighboring circles to their right. Alright, so these 2 are given to this, these 3 are given to this. So I'm going to use this kind of diagram. The rightmost item cannot be a stick. It has to be a circle. Because we need to give all those energy quanta to the particles. Alright, so if you have a stick at the end, that means this stick is not given to any particle. Alright, so that's not the scenario we analyze. We are analyzing all this m energy quanta shared among n particles. So this one is a little special. We have to have a circle at the end. We have an array of sticks and circles from left to right, but the rightmost item must be a circle or a particle to accept energy quanta. So this is fixed. Now you probably can see why we have n minus 1 in the end, n minus 1 over here, because we need to put 1 particle at the end. Alright, and then we will actually look at the permutations of the remaining items. We have 11 sticks and we have 8 minus 1 circles. Alright, 11 sticks and 7 circles. We have a total of 18 items right before the last circle. 18 items. The number of permutations of 18 items is 18 factorial. So now we have this on top, 18 factorial on top. The number of sticks, 11, plus number of circles, 8 minus 1, because we need one at the end. We cannot change that fact, so we have 18 factorial on top. And then we divide this 18 factorial by 11 factorial, because among this 11 energy quanta we can do permutations. You'll get the same scenario. So 18 factorial over 11 factorial. Now let's look at this 7 open circles. We can also do permutations of this 7 circles, and that's not going to change our diagram. For example, if I swap the first one and the third one, I swap these 2 circles, does that make any difference? No. Yes, if I swap these 2 circles or these 2 circles or these 2 circles, any different? No. So we're going to divide 18 factorial by 11 factorial and divide it by 7 factorial. Now we have this equation. Alright, and for this specific case, when we assign 11 energy quanta to 8 molecules or 8 atoms, there are this many different ways, 31,824 ways to do that. We can easily numerically verify this equation with simple examples. If we give 3 energy quanta to 3 molecules, we plug in 3 here, 3 here. Alright, we have 5 factorial over 3 factorial over 2 factorial, we get 10 microstates. It's indeed 10. I mean, we can even count this 10 really easily. When you give 3 energy quanta to 3 molecules, we can have 300, right? We can have 210, 201, 120, 102, 012, 021, right? And also we can have 111. And I forgot to mention, you know, when I said 300, we can also have 030 and 003. So a total of 9 microstates. What if we have 4 energy quanta distributed among 3 molecules? Alright, we have 15 microstates. You just plug in 4 here, 3 here, 4 here, 3 here. And you get 6 factorial over 4 factorial over 2 factorial, it's 15. And we can quickly count this 15 microstates among 3 molecules. So we can have 400, 040, 004. Right? And then we can have 310, 301, 130, 103, 031, and 013. And then we can have like 220, 202, 022, right? And then we can have 211, 121, 112. So if you sum up everything, you get 15 microstates. And now here's the numerical example. What if we have a canonical ensemble? Alright, let's say we have 25 particles, and I'm going to plot the relative population for different ensembles with this many energy quanta. Again, canonical ensemble means NVT are constant. The number of particles is 25, the volume is constant, and the temperature is constant. However, we can have energy oscillation. Alright, so that's why I'm putting a range here. The energy can be from 0 to 50. Again, the energy can be from 0 to 50. It's just the I can only put 16 of them here. We can compute the number of microstates. If you have 25 particles sharing 0 energy quantum, and we just have 1 microstate. What if you have 1 energy quantum? Well, we can give this one to any one of this 25 particles. Therefore, we have 25 microstates. Now, what if you have 2 energy quanta? Now it's kind of complicated. I will just use this equation. I'm going to use the factorial of 2 plus 25 minus 1 factorial on top. And then 2 factorial on the bottom, also 25 minus 1 factorial on the bottom. Alright, and then we get 325. Okay. And after that, we have 3 energy quanta, 2000 something. It's a little hard to calculate, but really the formula is easy. You have 3 plus 25 minus 1 factorial divided by 3 factorial divided by 25 minus 1 factorial. So over here I have the equation that I used in this spreadsheet. When we keep going, you can see the number of microstates going up. the more energy you have, the more ways you can distribute those energy to 25 particles. And now we need to look at the Boltzmann distribution. So in this case, when energy goes up, the Boltzmann distribution, you can see the exponential function goes down from 1 to 1.1 times 10 to the power of negative 7, so really small. How do we do this? It's pretty simple. We're assuming like kBt is just 1 epsilon. So over here it's e to the power of negative 0, e to the power of negative 1, e to the power of negative 2, e to the power of negative 3. Over here, this is e to the power of negative 16. Now let's look at the weight over here. How do we get this, the weight over here? It's pretty simple. We'll just do this. We'll just do this, multiply by this. We get this number 125 times 0.368. I got 9.2. 325 times 0.135. We get 4.4. So this weight is simply the product of the number of microstates associated with some energy and the Boltzmann exponential function associated with the same energy. Alright, now let's look at this. When we multiply this, I don't know, this one is roughly 6 times 10 to the power of 10, and this is 1 times 10 to the power of negative 7, so the product is this. Alright, and now what we can do is we can examine all those weight. The weight goes up, you know, you can see the number goes up. Just look at the order, it goes up, right? But now let's look at the number more carefully. When does it reach maximum? I think somewhere here. Alright, between this n equals the quanta equals 13 and 14. We have the maximum. Alright, we have the maximum here, over here, around here. It's about 8,000. The weight reaches maximum, and then it drops to 7.7, 7.1. And again, just because I cannot put all 50 rows on this slide, so there are 34 more rows. So in the end, you know, you can see the weight goes up. Over here we have 13 and 14 over here, and then it goes down. Eventually, when it reaches 250, the weight is going to be really small. When you have 50 energy quanta, again, this the number of microstates is going to be huge, but this exponential function is going to be really small. Just imagine what is e to the power of negative 50. E to the power of negative 50 is a really small number. I think it's roughly 10 to the power of negative 22. So that's why the weight goes up first and then goes down. Alright, you have this kind of curve. You have a maximum. The peak is around 13 or 14. So you can see these two weights are the maximum. Now let's do weight times E. So we're going to calculate the average energy over here. So this is weight times E. We get all those numbers. And then weight averaged E. So that means we need to sum up all those numbers and then divide it by the sum of the weight. I got 14.55 epsilon. Alright, so all those ensembles, we can see different energy in different ensembles between 0 and 50. Alright, actually it can be 51, 52. It's just after this it's going to be negligible. Alright, so I only calculated it from 0 to 50 energy quanta. The weight reaches the maximum around 13 or 14, and the weight average energy in epsilon is 14.6. So what I did is I did the sum of this row or this column of weight times energy divided by the sum of this column of weight, and I get the weight averaged energy. And you can see the maximum is really close. 13, 14 is really close to 14.5. Again, this is just a numerical example. You know, if you have 25 particles, assuming they can have different energy from 0 epsilon to 50 epsilon. You have this distribution. You have the weight here. The maximum weight is around here between 13 and 14. The average energy is 14.55 epsilon. So this here between 13 and 14, let's say 13.5 ish, is very close to 14.5 for this 25 particle system. Now let's increase the number of particles to 50. So what will happen is this. Now we have more particles. When there's no energy, there's only one microstate. When there's one energy quantum, there are 50 microstates, right? Because each of the 50 particles can get this energy quantum. When there are two energy quanta, that's more complicated. I will do just 2 plus 50 minus 1 factorial over 2 factorial over 50 minus 1 factorial, and get this number 1275. And I keep doing this for a total of 51 rows from 0 epsilon to 50 epsilon. And now this is Boltzmann exponential function. It's pretty simple. It's e to the power of negative energy over kBt. We were assuming h epsilon is kBt, and then this is e to the power of 0, e to the power of 1 over here. This is e to the power of negative 17, and we keep doing this. We get e to the power of negative 50, etc., etc. And we got this weight column. The weight column is the number of microstates times the Boltzmann exponential function, and we can just examine all those numbers. It just keeps going up until 17, because when you really look at this graph, it keeps going up until around 30. So at around 30, it reaches the maximum. All right, and the distribution is like this. Right. Now let's look at the average energy. We need to have the sum of this column of weight times energy divided by the sum of this column of weight. The average weight, the weight averaged energy in epsilon is 29. So 29 epsilon. Most replicas have an energy of 29 epsilon or close to it. All right, or very close to it. So I just want to emphasize this. When we have a MVT canonical ensemble, it's possible for the system to undergo energy exchange with its surroundings. That's why the energy of a MVT ensemble can have different energies, in this case from 0 to 100 epsilon. But really over here, you see the population or the weight or the probability of finding an ensemble reaches the maximum when its energy is really, really close to the average energy of all replicas. Now let's do some mathematical analysis. We define the partition function Q as follows. Alright, so we're going to just define this Q to be the sum of the Boltzmann exponential function. The Boltzmann distribution function is e to the power of negative energy over kBt. And we're define beta to be 1 over kBt. It's just for convenience. So Q is the sum of e to the power of negative beta epsilon I. Alright. If we have a 2-unit ensemble, that means we have only 2 replicas. We can prove this. Well, this uppercase Q, that is the canonical partition function of the entire ensemble. It's the product of the lowercase q sub a times the lowercase q sub b, which is q squared. The proof is as follows. So q sub a is for replica A, q sub b is for replica B. So qa times qb is this sum times this sum. When you do this sum times this sum, alright, you will be able to evaluate the product, which is just this. Alright, you can kind of verify this all by yourself. Over here you can see, let's say M is from 1 to 100, N is from 1 to 100. So you have 100 terms times 100 terms. Alright, and then you'll get 10,000 terms over here. Over here, M is from 1 to 100, N is from 1 to 100. So mathematically, we can just prove this is equal to this. Alright, again, if you really need a simpler example, it's just this. If we have a sum of 2 items and a sum of 2 items, we multiply this 2 sums, we get 4 items. Or you can say x1 plus y1, or x1 plus x2 times over here y1 plus y2, you get x1 times y1, you get x1 times y2, you get x2 times y1, you get x2 times y2. So that's a simpler mathematical example to convince you this equation holds. Now you can see this uppercase Q, which is the canonical partition function for the entire ensemble. It's just the product of the partition functions for every replica. There are 2 different scenarios. If you have distinguishable ensembles, the uppercase Q is simply Q to the power of n. But what if the ensembles are indistinguishable? Somehow we cannot view the n factorial permutations as n factorial different ensembles. And then that means we have to have this Q sub n, Q to the power of n, divided by n factorial as the number of permutations with n replica with the same scenario inside. Again, if you have n units, we can have n factorial different permutations. We're going to view this n factorial permutations as the same replica. Well, it's just counted as just one. Many particles, such as electrons, are indistinguishable. So eventually, when we count the number of microstates for those quantum particles, we'll keep this in mind. At certain stage, we need to divide the total number of microstates we counted divided by n factorial, where n is the number of particles. We'll have to do that. For molecules, there are 4 different types of partition functions, including 3 for nuclei and 1 for electrons. The 3 partition functions for the motions of nuclei are here: translation, rotation, and vibration of nuclei. You can also say they are translation, rotation, and vibration of molecules, because when we are looking at the translation, rotation, and vibration of molecules, mostly those are the motions of the nuclei. The electron just move accordingly. Finally, we have a partition function for electrons. It's called electronic partition function. It includes the potential and the kinetic energy of electrons, and also, just by convention, when we say electronic energy, sometimes we are including the nucleus repulsion in this electronic energy. All right, it's just convention, or we just call that electronic energy. Now the partition function is multiplicative, so if you have molecule, you have translational partition function, rotational partition function, vibrational partition function, and electronic partition function. The product of these 4 will give you the total partition function of the molecule. The partition function of one replica in a canonical ensemble is therefore this. Now it's a little complicated. Q is the sum of e to the power of negative beta over times epsilon n. Epsilon n, well, it's the sum of the translational energy, rotational energy, vibrational energy, and electronic energy. And they can all have their own different energy levels. Like translational energy, you go from 0, 1, 2, 3, 4, 5. Oh, but wait. For translational energy, you cannot have a quantum number of 0. So you start with 1, and then 2, 3, 4, 5. Rotational energy levels, you can go from 0, 0, 1, 2, 3, 4, etc. Vibrational energy, well, it's 1/2 plus n times h nu, and that n can be 0, 1, 2, 3, 4. And then electronic energy, well, whatever molecule you have, we can have many electronic energy levels. So we get this sum, and then we can separate this sum into 4 parts, the product of 4 different sums. Alright, so we have translational partition function here, rotational partition function, vibrational partition function, and electronic partition function. Beta is just defined to be 1/kBt for convenience. Now if we have a n-unit distinguishable ensemble, the uppercase Q is the lowercase q to the power of n. What if the ensembles are indistinguishable? Then we need to divide this whole thing by n factorial. Now let's derive the average energy of a particle in a many particle system at temperature T. Alright, we can calculate this if we know its partition function. The definition of the partition function is this: the lowercase q for this replica is the sum of the Boltzmann exponential function e to the power of negative beta times epsilon n. Beta is 1/kBt, epsilon n is just the different energy levels. The probability of a particle occupying energy level k is this. It's this Boltzmann distribution function at energy level k. And over here, those are the sum of all Boltzmann exponential functions at different energy levels. So we have the average energy, or weighted average energy, is this. It's the sum of the energy of each level multiplied by the probability of a particle in this level. So epsilon k is here, the probability is this. I'm going to just plug in this probability over here, and then we get this expression. Okay, we get this expression. It's the sum of epsilon k times this fraction. In this fraction, we have this on the bottom. And this thing on the bottom, this is simply q. Alright, this is simply q. And you can take q out of the sum because q is independent of the value of k here. So you can take the q out. Alright, and then after you take this q out, you have this expression, a sum of epsilon n times the Boltzmann exponential function, e to the power of negative beta epsilon n, and then divided by q. K and n are so-called dummy indexes. So really that means if you replace this n with alpha, you get the same sum. Alright, here's an example. If you calculate the sum of I from 1 to 3, you get 6. If you calculate the sum of alpha from 1 to 3, you also get 6. It does not matter what the dummy index you use. Same here. I mean, if you sum it up, for n equals 1 to infinity, it's the same as summing up this for alpha from 1 to infinity. Alright? Now, we got this equation, nice equation. The average energy is the sum of epsilon n times e to the power of negative beta epsilon n over q, and therefore q times the average energy is this sum. The sum of epsilon n times e to the power of negative beta epsilon n. So we get this equation. And somehow if we can evaluate q, and if we can evaluate this sum, we get the average energy. And we'll do that. It's pretty tricky. There's a mathematical trick about this. We want to get the sum of epsilon n times e to the power of negative beta epsilon n. How do we do that? Actually, we start with dq over d beta. So this is dq over d beta. Q is the sum of the Boltzmann exponential function. The derivative of a sum is the sum of the derivatives. So this is what I did from here to here. Alright, so if you're doing, for example, the derivative of x plus y, well, that's just the sum of the first derivative of x and the derivative of y. So this is true mathematically. And then we can evaluate this. It's really easy because we have exponential function over here, right? So we just copy this exponential function here and then use the chain rule. We should look at the derivative here, which is negative epsilon n. Also, from here to here, you probably realize why we define beta to be 1 over kBt. When you do this first derivative, it's really convenient. Alright, so it's just negative epsilon n from the exponential term multiplied by this exponential function. And remember, we did this only because in the previous page we see this expression is Q times the average energy. So this is just a negative Q times the average energy. Alright, so dq over d beta is just negative Q. This part is negative Q times the average energy. And therefore, the average energy is just negative dq over Q over d beta. And now dq over Q is d ln Q. Why is that? Because you can see d ln Q over dq is 1 over Q. Therefore, dq over Q is d ln Q. So the average energy is negative d ln Q over d beta. So that's a pretty simple expression over there. D beta, well, can be written as the differential of 1 over kBt because beta is defined to be the reciprocal of kBt. And when you do that, you can evaluate this divided by dt. Well, it's negative kBt squared, the reciprocal of this. So you can see my derivation over here. I'm just taking the derivative of beta, or 1 over kBt over dt. I get negative 1 over kBt squared. Alright, so this is dt times negative 1 kBt squared. And then because negative 1 kBt squared is on the bottom, we flip that up, and because there's a negative sign here, and there's a second negative sign here, for like division, they cancel. Now we have just a simpler expression for the average energy. Again, we have this equation from just calculus, and d beta is this, and d beta is simply negative 1 over kBt squared times dt. So we can replace this d beta with this. We can simplify everything. And now we have the expression for the average energy of the particle in an NVT, canonical ensemble. It's negative d ln Q over d beta. It's kBt squared d ln Q over dt. And also we can express this as kBt times d ln Q over d ln T. It's just because d ln T over dt is 1 over T. Therefore, we can just kind of move one of the two t's here to the bottom. You get dt over t. dt over t is d ln T. So we got this expression as well. So if we have the expression of Q in terms of beta or T, we can plug in that expression of Q in terms of beta here. We can plug in the expression of Q in terms of T here or here. And then we simply take first derivatives, alright, 3 different derivatives. We will be able to get the average energy of the particle. So the first thing is to determine the expression of Q, the partition function, in terms of beta or T. Chapter 25, Statistical Thermodynamics, Section 25.2, Translational Partition Function and Energy. The average translational energy of the particles can be determined given the translational partition function using the following equations. The average energy is negative d ln Q over d beta. The average energy is kBt squared times d ln Q over dt. The average energy is kBt times d ln Q over d ln T. So we just need to find out the expression of the translational partition function in terms of beta or t, and then we can plug in the expression of Q into these equations to get the average energy of the particle. For quantum translation in a one-dimensional box with a length of a, we have the energy levels here. The epsilon 1D translational energy is n squared h squared over 8 ma squared. H is the Planck constant, m is the mass of the particle, a is the dimension of the box, n is the quantum number, n is 1, 2, 3, 4, integer numbers. Now let's look at Q, the partition function of one-dimensional translation. It's the sum of the Boltzmann distribution functions e to the power of negative epsilon over kBt. Here, this epsilon is one-dimensional translational energy, and that's n squared h squared over 8 ma squared over kBt. So we need to evaluate this sum. This sum is approximately this sum. I only changed the index here from a 1 to a 0. So over here we have all those infinite number of terms from 1 to infinity. Over here I just added 1 over here. So this is a huge number. This huge number is approximately equal to itself plus 1, because when n is 0, this exponential function is 1. Again, if you have, for example, 10 to the power of 24 here, it's approximately the same as 10 to the power of 24 plus one additional term, 1. Now let's look at this one-dimensional translational partition function. It's written as a sum over here, but now it's written as integral here. So how can we go from sum to integral? Well, if you look at the integral, well, the integral value is simply the area under a function curve. And the area under a function curve can be decomposed into many bars, right, with a width and height. And if we have a really large number of bars and narrow enough bars, we can see the sum of the function is approximately the same as the integral of that function. So that's what I did over here, from here to here. What I'm doing is I'm trying to approximate this sum by using an integral. The reason is it's very difficult to actually get the sum, but it's easier to evaluate this integral. And again, this approximation is quite reasonable because we're simply looking at a infinite number of terms with a infinite number of bars and with very narrow bar width. Going from here to here, we simply used the properties of Gaussian functions. They are even functions. That means the integral of a Gaussian function is simply just 2 times the integral of this Gaussian function of just one side. You can always divide a Gaussian function into 2 parts, from negative infinity to 0, and then from 0 to positive infinity. Alright, so this is from over here 1/2 of the entire Gaussian function to the entire Gaussian function. That's why I put 1/2 over here. We just need to evaluate this. How do we do that? We need to use a variable substitution. We simply set alpha to be h squared over 8 ma squared kBt. So over here, h squared over 8 ma squared kBt is alpha. Now we get this equation. Alright, and we're not done yet. We still want to further simplify this equation as well. We will just put a square root of alpha here, and then divided by square root of alpha here. The reason is we're about to set a new variable to be equal to square root of alpha times n, and then this is going to be e to the power of negative that variable squared. So again, the one-dimensional translational function is 1/2 of this integral of this Gaussian function from negative infinity to positive infinity. And I multiply this n by the square root of alpha, and then divide the square root of alpha here. Now I set z to be the square root of alpha times n, and then this one-dimensional translational function is simply 1/2 times square root of alpha, and we just need to integrate a Gaussian function from negative infinity to positive infinity. This integral is the square root of pi. We can prove this if you know how to convert the Cartesian coordinates to polar coordinates in a two-dimensional space. So we can prove this part squared is actually pi. But let's just use the conclusion here. This integral is the square root of pi, and therefore the one-dimensional translational function is the square root of pi over 2 times the square root of alpha. Alpha is defined to be h squared over 8ma squared kbt. And we clean up this a little bit, we get the square root of 2 pi m kbt a squared over h squared. So it's just algebra from here to here. It's simply algebra. And now we get this expression for one-dimensional translation. It's the square root of 2 pi m kbt, and then multiplied by the length of the box over the Planck constant. For a quantum translation in a three-dimensional box with the psi length of a, b, and c, the 3D translational partition function is the product of the three individual one-dimensional translational partition functions. So over here, this 3D q is equal to this in the, for example, x direction, and then this partition function in the y direction, and then this partition function in the z direction, and then we just do the multiplication. We have now 2 pi m kbt to the power of 1.5. And then we multiply a, b, and c together over h to the power of 3. And a times b times c is simply the volume of the three-dimensional box. So now the three-dimensional translational function is 2 pi m kbt to the power of 1.5 times the volume over h cubed. The three-dimensional translational partition function is written as q superscript 3D and subscript translation. This is proportional to the volume of the container, and it's proportional to temperature to the power of 1.5. Now let's use the partition function to get the average energy. The average three-dimensional translational energy of the particle is kbt squared d ln q over dt. We're going to use just this equation out of the three. We can use any one of the three equations. It can be d ln q over d beta. It can be d ln q over dt. It can be d ln q over d ln t. So just whatever you do, just use the equation, the corresponding equation exactly. Right now I'm using d ln q over dt, so this has to be multiplied by kbt squared. If you do d ln q over d beta, I think you need a negative sign. If you do d ln q over d ln t, the result should be multiplied by just kbt. So anyway, I'm using this equation and this equation. So either way, you can use either one of these two. You can use d ln q over d beta times -1 as well. But right now, it seems more convenient just to do one of this. The average energy is kbt squared times d ln q over dt. And now look at this function. This function contains temperature here. But that's pretty much it. So we can decompose this logarithm into the sum of two logarithms. This logarithm is the logarithm of a t to the power 1.5 plus the logarithm of everything else. So over here it's just a constant times t to the power 1.5, and that's why I can separate this two here. And now look, the logarithm of everything else is independent of temperature, so this derivative is just 0. We just need to look at this one. And when we look at this one, we have this expression. And how do we do this? Well, it's pretty simple. The logarithm of t to the power 1.5 is simply 1.5 times ln t. And the first derivative of ln t is 1 over t. So that's why we have 1.5. We have 1 over t here. Multiplied by this kbt squared. Now we get 1.5 kbt. The average translational energy of the particles is 1.5 kBt. I used the particle in the box model and get this expression. The average three-dimensional translational energy is 1.5 kBt. The molar three-dimensional translational energy is this. Okay, so it's just Avogadro constant times 1.5 kBt. We get 1.5 RT. Don't forget that we made some assumptions in the derivation. We're assuming those are free particles in the box. That means they don't feel any attraction or repulsion. That means we're dealing with ideal gases when we derive this. Okay, for ideal gases, no attraction, no repulsion. They are considered free particles in the three-dimensional box. The average translational energy is 1.5 kBt, and then the molar three-dimensional translational energy is 1.5 RT. And what if there is attraction or repulsion? Then we need to modify the expression of the energy levels, because the energy is going to include both the kinetic energy and attraction and repulsion. Again, R is simply the Avogadro constant times the Boltzmann constant. Similarly, we can derive the one-dimensional translational energy as well, per particle and per mole. So really, you just need to use the one-dimensional translational partition function here. I think it's the square root of 2 pi m kBt multiplied by A over H. When you do that, you'll get just 1/2 kBt. Alright, so in that case, one-dimensional translational energy has an average value of 1/2 kBt. The molar one-dimensional translational energy is going to be 1/2 RT. Chapter 25, Statistical Thermodynamics, Section 25.3, Rotational partition function and energy. The average rotational energy can be determined given the rotational partition function using the following equations. The average energy is equal to negative d ln q over d beta. The average energy is kBt squared d ln q over dt, or kb times t times d ln q over d ln t. If we use the rotational partition function here, we'll get the average rotational energy. For the three-dimensional rotation of a linear molecule, such as H2, HCl, and HCN, the rotational energy levels are J times J plus 1 times H bar squared over 2I. J can be 0, 1, 2, 3, etc. For a diatomic molecule, I, the moment of inertia is mu times R naught squared. Mu is the reduced mass. 1 over mu is 1 over m1 plus 1 over m2. For a linear polyatomic molecule, I is the sum of mi Ri squared. Here R sub I is the distance between the mass m sub I and the center of mass of the molecule. The rotational partition function for a linear molecule is the sum of 2j plus 1 times this exponential function, e to the power of negative j times j plus 1 times h bar squared over 2I over kBt. Or it can be written as the sum of 2j plus 1 times e to the power of negative j times j plus 1 times h bar squared over 2I kBt. I just placed this 2I on the bottom. J is the rotational quantum number. J can be from 0 to infinity. The degeneracy of the jth rotational energy level is 2j plus 1, because the z component quantum number, m sub j, can adopt 2j plus 1 different values. M sub j can be negative j plus 1, etc., all the way to j. Again, the rotational partition function of a linear molecule is the sum of 2j plus 1 times e to the power of negative rotational energy over kBt, or j times j plus 1 times h bar squared over 2I divided by 2kbt. It's extremely difficult to get the sum right. So we make an approximation here. We assume this integral of the same function is equal to the sum over here. We have this rotational partition function of a linear molecule approximately equal to the integral of 2j plus 1 times e to the power of negative rotational energy over kbt dj. J is from 0 to infinity. We will simplify this integral by doing variable substitution. We can set jx to be j squared plus j. Therefore, dx is simply 2j plus 1 times dj. And we do see 2j plus 1 times dj here. That becomes dx. And on top, j times j plus 1 becomes x. Since j is from 0 to infinity, x should also be from 0 to infinity. So we have this integral here. It's not simple enough. We now set z to be h bar squared times x over 2I kbt. And then this function becomes e to the power of negative z. Meanwhile, x is 2I kbt over h bar squared times z. Therefore, the rotational partition function of a linear molecule becomes this 2I kbt over h bar squared times the integral of e to the power of negative z dz. And z is also from 0 to infinity. The integral of e to the power of negative z is negative e to the power of negative z. We can plug in infinity and 0, take the difference. The result is 2I kbt over h bar squared. Or we can write this as kbt over h bar squared over 2I. And remember, we defined this rotational constant in a way that hcb is equal to h bar squared over 2I. So the rotational partition function for a linear molecule can also be written as kbt over hcb, only because we defined b so that hcb is equal to h bar squared over 2I. Again, hcb is equal to h bar squared over 2I. B is the rotational constant. B is h bar squared over 2I over hc, or h over 8 pi squared ci. C is the speed of light, I is the moment of inertia, and h is the Planck constant. After the inversion symmetry of the linear molecule is considered, the rotational partition function of a linear molecule should be kbt over sigma hcb. So what is this sigma? It's the symmetry number. For a linear molecule with an inversion center such as H2, sigma is 2 because of the indistinguishability of the rotation of the molecule at 0 degrees and 180 degrees. For linear molecules without an inversion center, such as HCN, sigma is just 1. So if we look at a linear molecule, it belongs to either D infinite H point group or C infinite V point group. If it's D infinite H, sigma is 2. If it's C infinite V, sigma is 1. We have the symmetry numbers for different point groups. If we have a point group C1, Ci, Cs, or C infinite V, sigma is 1. When we have rotational axis Cn, Cnv, Cnh, sigma is n. For D infinite H point group, sigma is 2, because if you rotate H2 180 degrees, you will get exactly the same configuration. For Dn, Dnh, Dnd, sigma is also 2n, 2 times this. some higher symmetry point groups. For T or TD point group, sigma is 12. For OH point group, sigma is 24. For IH exohedral point group, sigma is 60. Finally, this S2N point group, sigma is n. For example, when we study the homonuclear diatomic molecules or any other linear molecules that belong to D infinite H point group, we must consider the fact that rotation about 180 degrees simply interchanges two equivalent nuclei. That means no difference, because the new orientation is indistinguishable from the original orientation. We must divide the rotational partition function by 2. Sigma is 2, so that indistinguishable orientations are counted as only one correctly. For heteronuclear diatomic molecules or any other linear molecules that belong to C infinity V point group, rotation by 180 degrees produces a different orientation. Therefore, sigma is just 1. We do not have to make any corrections regarding symmetry. In CH4, if we allow free rotation of the hydrogen atoms, there are 12 possible arrangements or orientations. Therefore, sigma is 12. And this is because when the 4 hydrogen atoms are labeled, there are actually 4 factorial, which is 24 different permutations. But among this 24 permutations, for the 4 labeled hydrogen atoms, for example A, B, C, and D, half of them, that means 12 permutations, are identical via rotations and should be counted as just 1. The other half of the 24 permutations are the enantiomers of the first 12. So this 12 is considered just one orientation, and this 12 are considered another orientation. The rotational partition function of a linear molecule is this: kBt over sigma hCb. Sigma is the symmetry factor. Now we're going to look at the average rotational energy for a linear molecule. It's going to be kBt squared d ln q over dt, and this q is the rotational partition function for a linear molecule. We plug in the expression over here. Q is kBt over sigma hCb, and this is logarithm, so we can separate this logarithm into 2 different logarithms. One contains temperature, the other does not. This part does not depend on temperature. Therefore, we just need to evaluate d ln t over dt. That's 1 over t. And then the final result is simply kBt. For a linear molecule, the average rotational energy is simply kBt. The molar rotational energy is simply RT, because kB times the Avogadro constant is R. Without showing the proof, the rotational partition function for a nonlinear molecule is this. We have a constant here, the square root of pi over sigma, and then multiplied by kBt over hCb1 to the power 1/2, kBt over hCb2 to the power 1/2, kBt over hCb3 to the power 1/2. B1, B2, and B3 are the 3-dimensional rotational constants. And this whole thing can be written as a constant times t to the power 1.5, because we have t to the power of 1/2, t to the power 1/2, t to the power 1/2, 3 times. So everything else becomes this constant c. And then we have t to the power 1.5. That's the rotational partition function for a nonlinear molecule. Now let's look at the average rotational energy of a nonlinear molecule. Again, we just need to do this kBt squared d ln q over dt. Ln q is ln c, the constant plus the logarithm of t to the power 1.5. And L and C does not depend on t. Over here we have 1.5 times dln over dt, which is 1 over t. Now the result is 1.5 kBt. The molar rotational energy is 1.5 RT because kb times the Avogadro constant is R. Why 1.5? So when we are looking at three-dimensional rotation of nonlinear molecules, the rotation can be done about the x, y, and z axis. So for the rotation about each axis, the average energy is 1/2 kBt. And we have 3 of them, therefore we have 1.5 kBt. For a linear molecule, assuming the molecular axis is the z-axis, then we have rotations about only the x and y axis. The rotation about x is 1/2 kBt. About the y-axis, also 1/2 kBt. So we sum up these two 1/2 kBts. We get 1 whole kBt over here for the rotation of a linear molecule. Chapter 25, Statistical Thermodynamics, Section 25.4, Vibrational partition function and energy. For a diatomic molecule with the harmonic oscillator approximation, the vibrational energy levels are this: h nu times n plus half. N can be 0, 1, 2, 3, 4, etc. When n is 0, we have the 0-point vibrational energy, which is 1/2 h nu. For convenience, we use the 0-point vibrational energy 1/2 h nu as the zero reference. The vibrational energy levels now become just n times h nu. N is 0, 1, 2, 3, etc., relative to 1/2 h nu. The diatomic vibrational partition function is therefore the sum of e to the power of negative n h nu times beta. Beta is 1 over kBt. It's easy to evaluate this. We first expand the sum to be 1 plus e to the power of negative h nu beta plus e to the power of negative 2 h nu beta plus e to the power of negative 3 h nu beta, etc. Both sides of this equation multiplied by e to the power of negative h nu beta, we'll get this: e to the power of negative h nu beta times the sum is equal to e to the power of negative h nu beta, so this 1 becomes this. E to the power of negative 1 h nu beta becomes e to the power of negative 2 h nu beta. E to the power of negative 2 h nu beta becomes e to the power of negative 3 h nu beta. And over here this becomes this, etc. And if you examine the sum of this, it's simply the sum of this minus 1. So it's just this series is simply this series minus 1. The second term here corresponds to the first term. Third term is the second term. Fourth term is the third term, etc. So we got this equation. And look, over here, this is simply Q. And this is simply Q. So really, we have e to the power of negative h nu beta times Q equals Q minus 1. Or you can say 1 minus e to the power of e minus h nu beta. So over here, I can simply combine this sum and this sum times e to the power of negative h nu beta. I can do this. This whole thing is just 1. If you look at this on the left, it's equal to this on the right. And then the sum is simply 1 over 1 minus e to the power of negative h nu beta. So the summary says if we use the 0-point vibrational energy as the zero reference, we have the vibrational partition function for a diatomic molecule. It's just 1 over 1 minus e to the power of negative h nu beta. Beta is the reciprocal of kBt. And we did make the harmonic oscillator approximation in the derivation. Again, the vibrational partition function of a diatomic molecule is this: 1 over 1 minus e to the power of negative h nu beta. For a nonlinear polyatomic molecule with n atoms and 3n independent coordinates, there are 3 translational modes, 3 rotation modes, and therefore 3n minus 3 minus 3. That's 3 minus 6 vibrational modes. The total vibrational partition function for such a nonlinear molecule is then this: the product of all those terms for different vibrational modes. We have 3n minus 6 vibrational modes. For a linear molecule with n atoms and 3n independent coordinates, there are 3 translational modes and only 2 rotational modes. Therefore, we have 3n minus 3 minus 2, which is 3n minus 5 vibrational modes. So the vibrational partition function of a linear molecule is the product of all those terms for all different vibrational modes. The vibrational partition function can be used to determine the average vibrational energy at temperature T relative to the 0 point vibrational energy, which is half h nu for each vibrational mode. How do we get the thermal correction for the vibrational energy? It's this: the average vibrational energy is negative d ln q over d beta. But again, after you calculate this, you need to add the zero reference, which is half h nu, as the 0 point vibrational energy over here. In this equation, since we're about to get the average vibrational energy, we need to use the vibrational partition function here. The vibrational partition function of a diatomic molecule with only one vibrational mode is this: the Q is equal to 1 over 1 minus e to the power of negative h nu beta. Nu is the vibrational frequency, beta is the reciprocal of kBt. We're going to use this equation. The average energy is negative d ln q over d beta. So we'll just evaluate this. And we plug in the expression of q. We get this. The negative sign disappears because this 1 minus e to the power of negative h nu beta is on the bottom in this fraction. So we have this one. And then how do we evaluate this? Well, it's pretty simple. We're going to use chain rule. So first it's logarithm, so we need to have the reciprocal of this part. So it goes here. And we copy this exponential function here, and then we take its the first derivative of the exponential term, which is negative h nu, and then negative h nu multiplied by another negative sign, so that's why we got this expression. The average vibrational energy is h nu times e to the power of negative h nu beta over 1 minus e to the power of negative h nu beta. And it can also be simplified to this: if we multiply the denominator and numerator by the same exponential function, e to the power of positive h nu beta, and then this becomes 1, and then on the bottom it becomes this: e to the power of h nu over kBt minus 1. So over here, this is the vibrational energy at temperature T relative to the 0 point vibration energy, which is 1/2 h nu. Together, the average vibrational energy at temperature T is this: the 0 point vibration energy 1/2 h nu, and then plus this part, so-called thermal correction. 1 over e to the power of h nu over kBt minus 1 times h nu is the thermal correction for the vibration energy. When temperature approaches 0, you can see this part approaches infinity, and this second term vanishes. We have the average vibration energy approach 1/2 h nu when temperature is 0K. The vibration energy at 0K is the so-called 0 point vibration energy. And over here, 0 point means the lowest possible. So 0 point vibration energy means lowest possible vibration energy, which is just 1/2 h nu. the molar vibrational energy is just 1/2 h nu multiplied by this Avogadro constant. At room temperature, kBt is 1.38 times 10 to the power of negative 23 joule per Kelvin times 298 Kelvin. This is roughly 4 times 10 to the power of negative 21 joule. For a typical vibrational wave number, usually the wave numbers are between several hundred to several thousand. So I'm going to just say 1000 wave numbers is typical. And we can compute the energy corresponding to this wave number. H nu is hc omega. And we can just plug in all the numbers, the value of H, the value of C, the value of omega. Over here, this is actually over here, this is supposed to be hc over lambda. And I'm using omega here to denote 1 over lambda, the wave number. But anyway, the calculation is correct. You get 2 times 10 to the power of negative 20 joule. So you can see this is 4 times 10 to the power of negative 21 joule. This is 2 times 10 to the power of negative 20 joule. And this is about 5 times this. So for a typical vibrational wave number, h nu is about 5 kBt. So when we evaluate this, 1 over e to the power of h nu over kBt minus 1 is roughly 0.007. So now you can see at room temperature, the vibrational energy, the average vibrational energy of a diatomic molecule is 1/2 h nu. This is the 0-point vibrational energy plus some thermal correction. The thermal correction is only 0.007 h nu. So this number is really close to just 0.5 h nu. The thermal correction to the vibrational energy is often negligible at room temperature, unless the vibrational wave number is much smaller than 1000 wave numbers. Now here's another example. If you have a small vibrational wave number, let's say around 200 centimeters, at room temperature, and then we do the same calculation. 1 over this minus 1 is 0.6. Alright, so it's 1 over e to the power of 1 minus 1, so e to the power of 1 is roughly 2.7, and then you do this, it's 1 over 1.7, roughly 0.6. Well, in this case, the thermal correction is very significant. The average vibrational energy of this diatomic molecule is 1/2 h nu plus the thermal correction, which is 0.6 h nu. In total, it's going to be 1.1 h nu. So when we are talking about vibrational energy, the thermal correction can be insignificant if the vibrational mode has a large wave number, such as 1000 wave numbers. Alright? But the thermal correction can be important if the vibrational wave number is small, for example 200. In between, we'll have to just make individual decisions. I would say if the wave number is more than 400, and then this is pretty small because we're looking at 1 over e to the power of 2 minus 1. It's fairly small. So as long as the wave number is above 400 or 500 wave numbers, I think we can assume this thermal correction is small. Again, the vibrational modes with small frequencies make more significant contribution to the average vibrational energy. It seems counterintuitive, but really molecules more likely appear in higher vibrational energy levels when the vibrational energy spacing are small. When the temperature is very high, or when the frequency is very small, we may have this kind of inequality. kBt may be much greater than h nu. Again, if you have really high temperature or really low frequency, you have this. In this case, h nu over kBt approaches 0. And now let's use Maclaurin expansion of exponential function. It's 1 plus x squared over 2 factorial. In this case, we can evaluate this using the truncated Maclaurin expansion of e to the power of x. We'll just cut it here, just 1 plus x. E to the power of x is roughly 1 plus x if x is small. You can verify this yourself. E to the power of 0.01 is roughly 1.01. Now we're going to use this approximation. E to the power of h nu over kBt minus 1 is very close to h nu over kBt if h nu is much smaller than kBt. Well, in that case, we have the average vibrational energy of a diatomic molecule, 1/2 h nu plus the thermal correction. And the thermal correction says this part is h nu over kBt, and then you have h nu divided by h nu over kBt is just kBt over here. Therefore, the thermal correction to the vibration energy is kBt at very high temperatures, or if the frequency is really low. Also, we need to assume the molecule is a harmonic oscillator and it does not dissociate at very high temperature. Each vibrational mode contains kinetic energy 1/2 kBt on average, and also potential energy 1/2 kBt on average at very high temperatures. So in total, you can say vibrational energy is kBt at high temperature, and 50% is kinetic energy on average. 50% of kBt is potential energy on average. The molar vibrational energy of a harmonic oscillator at very high temperature is this: Avogadro constant times the 0 point vibration energy 1/2 h nu, and then plus RT, because Kb times Avogadro constant is R. Now let's look at these two terms. The first term is from the 0 point vibrational energy, and the second term is the thermal correction if kBt is much greater than h nu. The vibrational partition function of a polyatomic molecule with more than one vibration mode is this: the partition function is the product of all those terms, and nu sub I is the frequency of the ith vibration mode. Beta is the reciprocal of kBt. The vibrational energy is the sum of the 0 point vibrational energy and the thermal correction. So we have a sum here. The average vibrational energy of a polyatomic molecule is the sum of 1/2 h nu plus 1 over e to the power of h nu over kBt minus 1 times h nu. And you need to do this for every single vibrational mode. So for example, if you have water, there are 3 vibrational modes. So you're going to have 3 such sums of 0 point vibration energy and thermal correction for the symmetric extraction, asymmetric extraction, and also bending in water. At 0K, we have a very simple equation. The vibration energy is simply the sum of 1/2 h nu I. So nu sub I is the frequency of the ith vibrational mode. At very high temperatures, assuming the molecules are harmonic oscillators, the thermal correction becomes kBt, and this is independent of the frequency. It's just kBt. So the vibrational energy of a polyatomic molecule at temperature T is going to be the sum over all vibrational modes, and for each mode we have 1/2 h nu plus kBt. This nu sub I is the frequency of the ith vibrational mode, and over here this kBt is independent of the frequency. Again, there are 2 terms. The first term is the 0 point vibrational energy for each vibrational mode. The second term is the thermal correction. when h nu sub I is much smaller than kBt. Chapter 25, Statistical Thermodynamics, Section 25.5, Electronic partition function and energy. The electronic partition function is this: Q sub electronic is equal to the sum of G sub I times e to the power of negative epsilon sub I of electronic minus epsilon sub 0 of electronic over kBt. Epsilon I of electronic is the electronic energy of the ith electronic state. Epsilon 0 electronic is the ground electronic state. And over here we take the difference between the ith electronic state and the ground electronic state. So we are essentially using the ground electronic state as the zero reference. G sub I is the spin multiplicity. Well, if you have a singlet, doublet, or triplet, G sub I is 1, 2, or 3. Here's an example. G sub 0 is 1 for H2, N2, helium-2, because for these three different chemicals. S is 0. 2s plus 1 is 1. They are singlet. So G sub 0 is 1 for the ground electronic states of H2, N2, and helium. Now for this H radical, fluorine radical, and OH radical, we have one unpaired electron. In the ground electronic state, S is 1/2. Therefore, 2s plus 1 is 2. It's a doublet. Then G sub 0 for these three radicals is 2. G sub 0 is 3 for O2 and B2. They are actually biradicals because in O2 you have 2 electrons occupying 2 degenerate pi star orbitals. In B2 you have 2 electrons occupying 2 degenerate pi bonding orbitals. In both cases, in the ground electronic state, S is 1, 2s plus 1 is 3, so we have a triplet for O2 and also for B2. Assuming the electronic energy spacings between the excited electronic states and the ground electronic state are much higher or greater than kBt, we then have this: electronic partition function is approximately G sub 0. Because if you look at this series of terms, the first term is G sub 0 times e to the power of negative 0 over kBt. These two cancel in the first term. So really the electronic partition function is equal to G sub 0 if we can neglect all those other terms. The average electronic energy at temperature T relative to the zero reference, which is epsilon sub 0 electronic, is this: we use negative d ln q over d beta. And if, again, we can assume the electronic energy spacings between the excited electronic states and the ground electronic state are much greater than kBt. And then out of all those terms in the series, we need to consider only the first term, which is G sub 0. So Q electronic is roughly G sub 0, which does not depend on beta. Therefore, this part is just 0. The average electronic energy is 0 relative to epsilon 0 electronic. And over here, we can also call this thermal correction. The thermal correction to the electronic energy is negligible in most cases. This is just because nearly all molecules occupy the ground electronic state at room temperature or even at very high temperatures. In very rare cases, for example, in a 3D transition metal. So over here, this D means d orbital. In 3D transition metal complex with nearly degenerate low and high spin states. And then we have at least two terms should be included in this electronic parting function. The first one is the ground electronic state. We have G sub 0, the spin multiplicity of the ground electronic state, plus G sub 1 times this exponential function. G sub 1 is the spin multiplicity of the first excited state. And this exponential function is this, e to the power negative epsilon 1 minus epsilon 0 over kBt. So epsilon 0 is the energy of the ground electronic state. Epsilon 1 is the first excited state. So if the difference between the ground and first excited electronic states is very small or comparable to kBt, we need to include the second term in this sum as well. Chapter 25, Statistical Thermodynamics, Section 25.6, Heat Capacity. The isochoric molar heat capacity is denoted by C sub Vm. It's equal to delta U sub m over delta T. U sub m is the molar internal energy. And we have this V in the subscript that denotes isochoric condition. The molar internal energy is the internal energy of 1 mole particles. Therefore, we have this equation, the molar internal energy is equal to the Avogadro constant times the average energy of one particle. We now evaluate the average energy of a particle at temperature T. It's the sum of the average translational, rotational, vibrational energies plus the average electronic energy. The first three terms, translation, rotation, vibration, they are the motions of the nuclei. The last term is the electronic energy. That includes the nucleus repulsion in here for convenience. For monatomic gases, the rotational energy is 0. The vibrational energy is 0. The average translational energy is 3/2 kBt. And this is the electronic energy. So we have this sum that contains only two terms, the average translational energy and also the ground electronic state energy. Monatomic particles do not possess any rotational or vibrational energy. We can easily get the isochoric molar heat capacity for monatomic gases. We just plug in this equation. It's delta U sub m over delta T on a constant volume condition, and that's N sub A times delta average energy over delta T, constant volume condition. And over here, the electronic energy does not depend on T. This is just the ground state electronic energy. I'm assuming the electronic energy spacing is much greater than kBt. So this part is independent of temperature. And over here, we just get 3/2 kB. 3/2 kB times the Avogadro constant is 3/2 R. So the isochoric molar heat capacity of monatomic gases is 3/2 R, assuming ideal gas behavior. It's just because when we derive this part, when we derive the average translational energy, we assumed ideal gas behavior. The isobaric molar heat capacity of monatomic gases is simply 5/2 R, just because CPM equals CVM plus R for ideal gases. The isochoric molar heat capacity CVM is delta U sub m over delta T on a constant volume condition. The molar internal energy is the sum of the 1 mole particles divided by mole, and therefore the molar internal energy is simply the Avogadro constant times the average energy of one particle. The average energy of one particle is the sum of the translational, rotational, vibrational energies of the nuclei. And also, we need to include the electronic energy as well. And again, over here, in this electronic energy, we include the nuclear repulsion for convenience, so that we have only 4 terms here. Otherwise, we'll have another term, which is the nucleus repulsion. Now let's look at diatomic molecules. Well, when you have diatomic molecules, we have rotations, we have vibrations. Therefore, we have 4 terms over here being non-zero. The first term, translational energy, on average 1.5 kBt. Rotational energy 1 kBt. Because really it's only 2-dimensional rotation. The rotation about the molecular axis does not count. Vibration, 0 point vibration energy plus the thermal correction. We got this thermal correction from the section on vibrational partition function and energy. And over here, it's just epsilon 0 electronic, which is just the energy of the ground electronic state. We can combine the first 2 terms, and we get 5/2 kBt plus 1/2 h nu, 0 point vibrational energy. This is the vibrational thermal correction, and over here this is just the ground electronic energy, which includes the nucleus repulsion. We can then get the molar isochoric heat capacity. It's simply delta U sub m over delta T, and then we just look at this. We take its first derivative with respect to temperature, and then multiply by the Avogadro constant. And from this, we get 5/2 R, and this term disappears because this does not depend on temperature. This term also is independent of temperature. So we need to take the derivative of this part over here with respect to temperature, and then multiply by Avogadro constant. For most diatomic molecules, we'll just get 5/2 R, or 2.5 R for most diatomic molecules, unless you're looking at molecules with very low vibrational frequency, and then this part can be significant. So for example, if we are looking at chlorine 2, I think chlorine 2 has a very low vibrational frequency, and therefore its molar isochoric heat capacity is going to be much larger than 2.5 R for that reason. So really we need to look at this and see if this part can be neglected. If you have a vibrational wave number higher than 400, 500 wave numbers, this part can usually be neglected. For linear polyatomic molecules, again we have 4 parts: translational, rotational, vibrational energies of the nuclei plus the electronic energy. And since it's linear, this part is 1.5 kBt, this part is just 1 kBt, together 2.5 kBt. Vibrational energy, since it's linear, we have 3n minus 5 vibrational modes. For each vibrational mode, we have the sum of the 0 point vibration energy and the thermal correction. And finally, electronic energy of the ground electronic state. Again, we're assuming the excited states do not matter, just because usually the electronic energy spacings are much greater than kBt. So most molecules, nearly all of them, are in the ground electronic state. Again, N, this uppercase N is the number of atoms. We have a total of 3 motions, and we need to subtract the 3 translational motions, 2 rotational motions. Therefore, we have 3 and minus 5 vibrational motions. For nonlinear polyatomic molecules, we have almost the same expression, except for nonlinear polyatomic molecules, now there are 3 rotational modes. So we have 1.5 kBt for translation and also 1.5 kBt for rotation. Together it's going to be 3 kBt. So look at the difference here. It goes from 2.5 to 3 because now we have 3 rotational modes versus only 2 rotational modes. We do have one less vibrational modes. It's 3 and minus 6 now, because we have 3 trans and 3 rotations. Therefore, we have 3 and minus 6 vibrational modes. And again, electronic energy. At 0K, the average energy of nonlinear molecules is simply the sum of 1/2 h nu plus electronic energy. Why? When temperature is 0, this is 0. When temperature is 0, this exponential function is infinity. 1 over infinity, that's 0. So we'll just get the 0 point vibrational energy plus the ground electronic state energy. The average energy of linear molecules is similar. It's just we need to change 3 and minus 6 to 3 and minus 5. That's the only difference. Now again, let's review this monatomic gases such as helium, neon gas. The average energy is 3/2 kBt or 1.5 kBt plus electronic energy. The molar internal energy is just Avogadro constant times this. We get 1.5 RT plus the Avogadro constant times the electronic energy. The isochoric molar heat capacity is therefore just 1.5 R, because this part does not depend on temperature. The derivative of this part is just 1.5 R. Really easy. Again, we assumed ideal gas behavior over here. When we derive actually the average translational energy, we did assume the ideal gas behavior. And for ideal gases, CPM is CVM plus R, so CPM is 2.5 R. Now let's look at a few examples. The values of the isochoric molar heat capacity of helium, neon, argon, they're all 12.47 joule per mole Kelvin. The CVM of atomic gas of a metal, such as mercury or sodium gas, is also 12.47 joule per mole Kelvin. It's not a coincidence. It's just because 1.5 R is 12.47 joule per mole Kelvin. R is 8.31446. The molar isochoric heat capacity of monatomic gas is only 1/2 in one of the 3 dimensions, but we do have 3 dimensions, so it becomes 1.5 R. Well, later we will learn this. Rotational molar heat capacity of a molecule is also 1/2 R for each rotational axis, about each rotational axis. For linear molecules, we have 2 rotational axes. Their rotational CVM is R. But if we have nonlinear molecules, we have 3 different rotational axes. Therefore, their rotational CVM is 1.5 R. Again, each translational molar heat capacity is just 0.5 R. Since we have 3 dimensions, the total is 1.5 R for translation. For rotation, it depends. Linear molecule, we have only 2 rotational motions. It's going to be R. For nonlinear molecules, we have 3 rotational motions. Therefore, its isochoric molar heat capacity is 1.5 R. For diatomic molecules in the gas phase, again, we have this expression. The average energy is, over here we have the average translational and rotational kinetic energy. Again, both translation and rotation are included in here. We have 1.5 kBt for translation and 1 kBt for rotation of this linear molecule. The second and third terms together are vibrational energy. 1/2 h nu is the 0 point vibrational energy, and this is the thermal correction of vibrational energy. Finally, electronic energy. The molar internal energy is simply the Avogadro constant times the average energy of a particle. So we get this term, 2.5 RT plus the Avogadro constant times the vibrational energy plus the electronic energy. So CVM is roughly 2.5 R if you just look at this term. Because h nu does not depend on temperature, electronic does not depend on temperature. Over here, although this does depend on temperature, the dependence is usually small as long as your vibrational wave number is more than 400, 500 wave numbers. So usually it's just 2.5 R. And again, we assumed ideal gas behavior, so CPM is equal to CVM plus R, 3.5 R. Here are a few examples. The CPM value of H2O2N2 are 28.8, 29.4, 29.1 joule per mole per Kelvin at room temperature. And they correspond to roughly 3.5 R, 3.5 R, 3.5 R. The CPM of diatomic molecules of much heavier elements may be notably greater than 3.5 R because of the more significant contribution from their low frequency vibrational mode. For example, the vibrational wave number of CO2 is only 560, and then the CPM of chlorine 2 is 3.98 R, so it's more than 3.5 R. But still, I think 3.5, 3.98 are fairly close to each other. For diatomic molecules in the gas phase, we have the molar internal energy, which is the molar translational and rotational energy over here, 2.5 RT, and then Avogadro constant times the average vibrational energy plus the average electronic energy. The vibrational thermal correction is this. The corresponding thermal correction to molar heat capacity and consequently molar isobaric heat capacity of diatomic molecule is this. We'll have to take the first derivative of this guy with respect to temperature. So it's really complex. We have negative n sub a times h nu over this guy squared because this is on the bottom, and then we use chain rule. We get the first derivative of this, which is simply e to the power of h nu over kBt over here. We copy that here, and we copy the exponential term h nu over kb from here, chain rule, and then negative 1 over t squared because this t appears on the bottom. Putting everything together, we get r times h nu over kBt squared, and on the bottom e to the power of h nu over kBt minus 1 squared, and then times e to the power of h nu kBt. We see h nu over kBt here, here, and here, so maybe we should pre-calculate h nu over kBt first and then plug it in. Let's look at chlorine. Chlorine has a wave number of 560 wave numbers. The experimental value of CPM is 3.98 R. It's not 3.5. It's more than 3.5. It's 3.98. Now let's make some theoretical prediction. Over here, let's compute h nu over kBt for chlorine 2. We can plug in this wave number to get frequency. From frequency, we get h nu over kBt. It's 2.7 at the room temperature. Alright, and then we evaluate this whole thing a lot, and it's r times, this is 2.7 squared, e to the power of 2.7 minus 1, and then squared, and then over here e to the power of 2.7. We get roughly 0.5 R. So the calculated CPM of chlorine 2 is 3.5 R without the vibrational thermal correction. And over here, this is vibrational thermal correction together. We predict its CPM is 4 R. Now let's look at the experimental value. 3.98 are really close to each other. So for chlorine 2, it's better to look at the vibrational thermal correction here for a more accurate isochloric molar heat capacity. For linear polyatomic molecules in the gas phase, again we have the average energy here. This is the average translational energy plus the average rotational energy. So 1.5 plus 1 kBt. And over here we have 3n minus 5 vibrational modes. And we have 0 point vibrational energy plus the vibrational thermal correction. And then electronic energy. Molar internal energy is Avogadro constant times the average energy. We get 2.5 RT plus the Avogadro constant times the average vibrational energy and electronic energy. Now let's look at CVM, CPM. CVM is the first derivative of this whole thing with respect to temperature. The 0 point vibrational energy does not depend on temperature. The electronic energy does not depend on temperature. This term, although it does depend on temperature, usually the dependence is small. So roughly the molar isochloric heat capacity is 2.5 R. CPM is R plus CVM, so 3.5 R. But if you have vibrational modes with small wave numbers, or if the temperature is pretty high, we do need to look at this term, the thermal correction, because this term can be more significant with small wave numbers or high temperature. Alright, in that case, well, CVM is greater than 2.5 R, CPM is greater than 3.5 R. So we actually studied chlorine 2. We see that CVM is roughly 0.5 R greater than this. CPM is also 0.5 R greater than this. Now let's look at nonlinear polyatomic molecules in the gas phase. Well, this time the average translational energy is 1.5 kBt. The rotational energy is also 1.5, so together you see 3 kBt here. This is the difference between nonlinear and linear. For linear, you have 2.5 kBt here. For nonlinear, 3 kBt here. We do have one last vibrational mode in nonlinear molecules. It's 3n minus 6 versus 3n minus 5 for linear molecules. And over here we have the vibrational energy. This is the lowest possible vibrational energy. And this is the thermal correction to the vibrational energy. Finally, electronic energy. And then we multiply everything by Avogadro constant. We get 3RT plus Avogadro constant times the average vibrational energy plus electronic energy. And then this is the molar internal energy. The isochloric molar heat capacity is delta U sub m over delta T. It's roughly 3R. Comes from here. And CPM is roughly 4R because CPM is R plus CVM. This part does not depend on temperature, and this part does not depend on temperature. This part does depend on temperature, but usually the dependence is fairly small, unless you have small wave numbers or very high temperature. And then we need to worry about this part, because this part can depend on temperature significantly. And then we need to kind of just include the derivative of this part with respect to temperature. Here are a few examples. The values of CPM of ammonia and CH4. They are both greater than 4R. So for ammonia, it's 4.22 R, greater than 4R. For methane, it's 35.7 joule per Kelvin per mole. It's 4.29 R, also greater than 4R at room temperature. So at room temperature, the isobaric heat capacity of ammonia and methane are both greater than 4R, just because of the contribution from the thermal correction to vibrational energy. And usually we look for the smaller wave numbers. In ammonia, in methane, we have vibrational modes that correspond to the change of the dihedral angle. And usually when you change dihedral angle, it does not require a lot of energy. That means we have small vibrational wave numbers. And actually those small wave numbers make the most contribution in here. They make great contribution to the vibrational thermal correction and also vibrational heat capacity. As a result, the CVM of ammonia and methane are greater than 3R. How much greater? Well, I think their actual isochloric molar heat capacity are greater than 3R by 0.22R and 0.29R respectively. And in turn, their CPM are also greater than 4R by 0.22R and 0.29R respectively. Chapter 25, Statistical Thermodynamics, Section 25.7, Entropy. For a system that contains n distinguishable particles which occupy m energy levels, assuming the Boltzmann distribution, the total number of microstates is given by this formula. W is equal to n factorial over a1 factorial, a2 factorial, a3 factorial, etc., all the way to a sub m factorial. N is the total number of particles in the system. A sub I is the number of particles in the ith energy level. So a sub I over n is equal to e to the power of negative beta epsilon I over the sum of e to the power of negative beta epsilon I. And we define the partition function q to be the sum of all those exponential functions. Therefore, a sub I over n is equal to e to the power of negative beta epsilon I over q. If we sum up all those a sub I over n, the sum would be 1. The probability of a particle occupying the ith energy level is denoted by P sub I. P sub I is equal to a sub I over n. P sub I is equal to e to the power of negative beta epsilon I over q. The occupation number of the ith energy level is n times pi. N times pi is also denoted by a sub I. Now let's look at Boltzmann's entropy equation. Boltzmann's entropy S is equal to the Boltzmann constant K sub B times the natural logarithm of W. W is the total number of microstates accessible to the system. Therefore, the Boltzmann entropy of this n-particle system is this. S is equal to K sub B times the natural logarithm of n factorial divided by a1 factorial, a2 factorial, a3 factorial, etc. And again, we're going to use the number of microstates associated with the Boltzmann distribution to evaluate W. So Boltzmann entropy is equal to Boltzmann constant K sub B times the natural logarithm of W. And W is the number of microstates. W is equal to n factorial over a1 factorial, a2 factorial, etc. a1, a2, a3, all the way to a sub m can be determined assuming the Boltzmann distribution. Now we can separate these two terms. So over here we have logarithm of something divided by something else. It becomes subtraction. So we have kb times the logarithm of n factorial minus the sum of the logarithm of ai factorial. So the logarithm of a product is the sum of different logarithms. Now let's use Stirling's approximation, which is ln x factorial is approximately x times ln x minus x. Now we replace this ln n factorial with n times ln n minus n. We replace every single ln ai factorial with ai ln ai minus ai. So we have the expression of entropy expressed this way. Now we noticed the sum of ai is n. So we have minus n here, we have minus negative n here, they cancel. Therefore we have only two terms left. It's going to be the Boltzmann constant multiplied by this, n times ln n minus the sum of ai ln ai. Now I'm going to expand this n. N is equal to the sum of ai. So I replace n with the sum of ai here. I just copied the second sum here. The reason is I like to combine these two sums. So after I combine these two sums, I get negative kb times the sum of ai ln ai over n. So if you just look at this, it's going to be the logarithm of n over ai. But I put a negative sign here. So now it's the logarithm of ai over n. Remember, ai over n is the probability of a particle occupying the ith energy level, denoted by pi. So ai over n is just pi. And ai is simply n times pi. Now we get this expression. I can take this uppercase n out of the sum because this n does not depend on I. Now we have this equation, and we can combine this n and kb because kb is the gas constant divided by the Avogadro constant, and the number of particles is the number of moles times the Avogadro constant. Therefore, we can rewrite this part as negative ni, nr. And if we look at the sum, it's a very simple expression. It's the sum of pi times the logarithm of pi. Therefore, the Boltzmann entropy is equal to approximately negative nr times the sum of pi ln pi. Pi is the probability of a particle occupying the ith energy level. Pi is ai over n. Pi is e to the power of negative beta epsilon I over the sum of e to the power of negative beta epsilon I. Pi is e to the power of negative beta epsilon I over q, where q is defined to be the sum of e to the power of negative beta epsilon I. Q is multiplicative, so Q is equal to the product of the translational Partition function, rotational Partition function, vibrational Partition function, and electronic Partition function. Epsilon, or the energy of a particle, is additive. The energy of a particle is its translational energy plus its rotational energy plus its vibrational energy plus its electronic energy. So over here, entropy is also additive. So the entropy of a system is equal to the total translational entropy plus the rotational entropy plus the vibrational entropy plus the electronic entropy. In general, the translational entropy is greater than the rotational entropy. The rotational entropy is greater than the vibrational entropy. The vibrational entropy is greater than the electronic entropy. Because P sub I depends on the relative energies of the particles, we can simplify the expressions of the vibrational Partition function and electronic Partition function by have some zero reference. We can define the 0K or 0 Kelvin internal energy as the zero reference. For convenience, the 0K internal energy, which is the sum of the electronic energy and the 0-point vibrational energy of the molecule, is just set to 0 when computing the Partition functions for vibrations and electronic Partition function. Again, Q is translational Q times rotational Q times vibrational Q times electronic Q. We have derived the translational Partition function. which is 2 pi m kBt to the power of 1.5 times the volume of the container over the Planck constant cubed. We derived the rotational partition function for a linear molecule, which is kBt over sigma hcb. B is the rotational constant, and sigma is the symmetry factor. If the linear molecule has an inversion center, sigma is 2. If the linear molecule does not have an inversion center, sigma is 1. So if you have a d infinity h point group, sigma is 2. If the point group is c infinity v, sigma is 1. What if we have nonlinear molecules? Well, then we have 3 different rotational constants, b1, b2, and b3. The rotational partition function for a nonlinear molecule is the square root of pi over sigma. Again, sigma is the symmetry factor. Now multiplied by kBt over hcb1 to the power 1/2, kBt over hcb2 to the power 1/2, kBt over hcb3 to the power 1/2. So the essential difference between linear and nonlinear is this. For a linear molecule, its partition function is proportional to t. For a nonlinear molecule, its partition function is proportional to t to the power 1.5. Now let's choose the 0k internal energy as the zero reference. More specifically, we're going to choose the lowest electronic energy as the zero reference. We're going to choose the 0-point vibrational energy as the zero reference, and therefore the electronic partition function is simply G sub 0. This is just the multiplicity of the ground electronic state. And over here, we also assumed that the excited states do not make any contribution to the electronic partition function. This approximation is very accurate as long as the electronic energy spacing is much greater than kBt, and that's usually true. For a linear molecule, we have 3n-5 vibrational modes. For a nonlinear molecule, we have 3n-6 vibrational modes. So we have the vibrational partition function as the sum of 1 over 1 minus e to the power of negative h nu I beta. For 3n-5 modes for a linear molecule, or 3n-6 modes for a nonlinear molecule. Again, a nonlinear molecule contains 3 rotational modes. A linear molecule contains only 2 rotational modes. And that's why we have a difference here and here. Now let's look at the derivation of Boltzmann's entropy. So previously we have entropy equals negative kBn times the sum of pi ln pi. So we can keep deriving this by replacing p sub I with e to the power of negative beta epsilon I over q. So over here pi is this, pi is replaced with this as well, e to the power of negative beta epsilon I over q. Now expand this. This is simply the logarithm of the top minus the logarithm of the bottom. The logarithm of the top is negative beta epsilon I. The logarithm of the bottom is just minus ln q over here. So we have this expression. We see negative sign, negative sign, negative sign, they cancel. So we have n times kb over here, and then q is independent of I. So I'm taking q out of the sum. So divided by q, and then the sum of this exponential function, e to the power of negative beta epsilon I times beta epsilon I plus ln q. Now we separate these two sums, and n times kb is just nr. So we replace n times kb with nr. And now let's look at the first term. The first term is beta over q over here, and then the sum of epsilon I times e to the power of negative beta epsilon I. The second term, ln q, is independent of the dummy index I. So I take ln q out, ln q over q, and then we have the sum of this. Now look at the sum of e to the power of negative beta epsilon I. This is simply q by definition. the partition function Q is defined to be the sum. So this two cancel, we have ln Q over here. What about this one? I'll just copy this sum over here. It's beta over Q times the sum of epsilon I times e to the power of negative beta epsilon I. And because Q is the sum of this exponential function, previously we derived dq over d beta, which is negative sum epsilon I times e to the power of negative beta epsilon I. So really this sum is equal to negative dq over d beta. And now let's look at a little bit more derivation. Let's look at this t times d ln Q over dt. Well, it's equivalent to kbt times dq over q over dkbt. How did I get this? Well, I simply multiply this t by kb and this t by kb. Kb and kb can cancel. d ln Q is dq over q. Why is that? It's just because d ln Q over dq is 1 over q. Therefore, d ln Q is dq over q. So we got this. kbt is 1 over beta. kbt is 1 over beta. Well, that's just the definition of beta. Beta is defined to be the reciprocal of kbt. Now we have this expression over here, and then what is this? d 1 over beta. It's this one is negative 1 over beta squared d beta. So we can clean up everything. We get negative beta dq over q d beta. It sounds really complicated, but if you look at this, this is equivalent to this or this. Why is that? Because dq over d beta is negative sum of epsilon times exponential function, right? So I'll just replace this dq over d beta with this whole thing. There's a negative sign here, they cancel. And then you have beta over q. We copy that here, and then we copy the sum here. So now you can see beta over q times the sum of epsilon I times e to the power of negative beta epsilon I is t ln Q over dt. So this whole thing, I was just proving this is equal to t times ln Q over dt. This part can be replaced with t times d ln Q over dt. So Boltzmann entropy is nr times t times d ln Q over dt plus ln Q. The molar entropy of the system is r times d ln Q over dt plus ln Q. We can even further simplify this. If you know d ln t is dt over t, we'll get an even simpler expression for the molar entropy. Molar entropy is equal to r times this sum, the sum of d ln Q over d ln t and ln Q. So it's not just ln Q, also it's the slope of ln Q versus ln t. You have two components here that make contribution to the molar entropy. So why do we have this? Again, it's just because d ln t over dt is 1 over t, and then we have this. Over here we have the equation for the molar entropy. It's r times t times d ln Q over dt plus ln Q. And this part can be written as d ln Q over d ln t. This is based on one assumption. We assumed all particles are distinguishable. But what if the particles are indistinguishable? In that case, the total number of microstates must be divided by n factorial, because for each combination of n particles, there are n factorial identical permutations. And all these n factorial permutations correspond to a single combination. For example, if 3 distinguishable particles occupy 3 different energy levels, and then you have a total of 6 possible arrangements. The number of microstates is 6. However, if the 3 particles are indistinguishable, let's say they are A, and A, they occupy 3 different energy levels, and then there's only one arrangement. We can say there's A in energy level 1, there's A on energy level 2, and there's A on energy level 3. And that's just one microstate. Therefore, when the particles are indistinguishable, we need to divide the number of microstates by n factorial. So the entropy should be reduced by this much accordingly. Now the expression for entropy is nr times T times dln(q) over dt plus ln(q) minus kb times the natural logarithm of n factorial. So it's just this part should be reduced correspondingly. And now we have this formula. Why do we have this? Well, it's just Stirling's approximation. Ln n factorial is n times ln minus n. And then we have a negative sign here, so we swap those. And then the uppercase n times kb is the lowercase n times r. Kb is r divided by the number of divided by Avogadro constant. And this n is the number of moles times the Avogadro constant. Now let's look at the molar entropy in more detail. The molar entropy is R times T times ln(q) over dt plus ln(q) plus 1 minus ln of the number of particles. Now we're going to separate this whole thing into 4 parts. The translational entropy, the rotational entropy, the vibrational entropy, and the electronic entropy. The indistinguishability goes in here for the translational modes. Right, again, we have molar entropy equals to R times this whole thing. That can be separated into the translational entropy, rotational entropy, vibrational entropy, and the electronic entropy. Again, Q, the partition function of a molecule, is the product of the translational partition function, rotational partition function, vibrational partition function, and electronic partition function. The translational partition function is 2 pi m kBt to the power of 1.5 times the volume divided by the Planck constant cubed. For linear molecules, the rotational partition function is kBt over sigma hcb. Sigma is the symmetry factor, b is the rotational constant. For nonlinear molecules, the rotational partition function is square root of pi over sigma times the square root of kBt over hcb1, the square root of kBt over hcb2, the square root of kBt over hcb3. If we choose the lowest electronic energy as the zero reference, electronic partition function is just G0, the spin multiplicity of the ground electronic state. If we choose the 0-point vibration energy as the zero reference, then the vibrational partition function is simply the product of 1 over 1 minus e to the power of negative h nu beta. For a linear molecule, we have 3n minus 5 different vibrational modes. For a nonlinear molecule, we have 3n minus 6 different vibrational modes. For an ideal monatomic gas, the rotational partition function is 1. The vibrational partition function is also 1. We just do not have rotations or vibrations. And therefore, the monatomic gas possesses only the translational entropy if the electronic partition function of this atom is just 1. So, for example, if you have helium, argon, xenon, in the ground state, those atoms have a spin multiplicity of 1, so G0 is just 1. Therefore, the electronic partition function is 1, assuming the energy spacing between the ground and excited electronic energy levels are much greater than kBt. And now we have only translational entropy. The equation is this. The first 2 terms are the molar entropy for distinguishable particles. What if you have indistinguishable particles? For example, if you have a bunch of helium atoms, they're indistinguishable. We need to make a correction. We need to have the molar entropy for distinguishable particles and then minus kb times the natural logarithm of n factorial. So therefore we see this here. The translational molar entropy is therefore this, after we replace the translational Poynting function with its expression here and here. This part is easy because we're taking the derivative of this function with respect to temperature. And this logarithm can be decomposed into the sum of two different logarithms. The first one is the logarithm of t to the power 1.5. The second logarithm is something independent of temperature. And then we can take the derivative, which is just 1.5 divided by t, and then multiply by t here, so it's just 1.5 over here. This part, we'll just copy it here, and then plus 1, and then minus ln n. N is the number of particles. Again, this derivative, this whole derivative is 1.5 divided by t, and then multiply by t here, you get 1.5. Now let's do some cleaning up here. 1.5 and 1, it's 2.5. And I see logarithm of v minus logarithm of n. I put them here. And then I see this 1.5 times the logarithm of 2 pi m kbt over h squared. So h squared to the power of 1.5 is h cubed. So from here to here it's just algebra. Now we have the translational entropy. The translational entropy is just n times the molar translational entropy. It's just n times r times everything inside the square bracket. 2.5 here, the logarithm of v over n, so, and then 1.5 times the logarithm of 2 pi m kbt over h squared. Using this equation, we can prove some equations in thermodynamics. In thermodynamics, we learned how to compute the entropy change in an isothermal expansion, going from initial volume to final volume. The entropy change of the ideal monatomic gas is this: final minus initial, and then we examine this. Only the term in the middle depends on volume. The other terms, they cancel, so we have this minus this, and therefore the result is nr times the logarithm of v final over v initial. We were able to prove this in thermodynamics. Now let's look at an isochoric process. So from T initial to T final. Now again, let's examine this term, they do not depend on temperature. Only here we have 1.5 times the logarithm of T. Alright, so we have 1.5 times the logarithm of T final, 1.5 times the logarithm of T initial, and then multiply by nr here and here. The result is 1.5 nr times the logarithm of temperature ratio. It turns out for monatomic gases, 1.5 nr is the value of C sub v. So the entropy change is C sub v times the logarithm of the temperature ratio. We also proved this in thermodynamics. So again, starting from this equation, in statistical thermodynamics, we can prove equations in thermodynamics, like this too. We can predict the standard molar entropy of ideal monatomic gases at room temperature, and actually any other temperatures or any other pressures. We just need to plug in numbers. First, this is the expression for molar entropy right here, and then V over N is RT over P over Avogadro constant. It's just because the uppercase N is the number of moles times the Avogadro constant, and then we know PV equals RT. We keep this equation here, so we just change V over N is equal to RT over P times Avogadro constant on the bottom. We can make it a little easier to calculate numerically because this m is the mass of just one particle, and Kb is a very small number. So I'm gonna just multiply this m by Avogadro constant. I'm gonna multiply this Kb by Avogadro constant. So this lowercase m becomes uppercase molar mass, and this Kb becomes R. And don't forget to divide the Avogadro constant twice on the bottom. Now we have this equation. Further, we can separate this T out, because I see a ln(t) here and 1.5 ln(t) here. So we copy 2.5 here. We have logarithm of r over p times Avogadro constant over here. We have ln(t) plus 1.5 ln(t). Well, now we have 2.5 ln(t), and then we have 1.5 times the logarithm of 2 pi mr over na squared h squared. So if you look at this equation, you can see the molar entropy depends on pressure and temperature. When we have higher temperature, higher molar entropy, higher pressure, lower molar entropy. Again, this uppercase m is the molar mass, but it has to be in kilogram per mole. If you try to do numerical calculations, it's easier to just use SI units. Now let's calculate the molar entropy for helium at room temperature and 1 bar. We're plugging all the numbers. So it's R times the sum of 4 terms, 2.5, the logarithm of R over P Na, 2.5 times ln(t), 1.5 times ln 2 pi mr over Avogadro constant squared h squared. So we're plugging all the values. R is 8.31446, 2.5 here, logarithm of R over the pressure and Avogadro constant, 2.5 times the temperature, and then 1.5 times 2 pi times the mass in kilogram per mole times R divided by Avogadro constant squared and h squared. All numbers are in SI unit. So in the end, I just get SI unit. I get 126.1 joule per mole per Kelvin as the molar entropy for helium at room temperature and 1 bar condition. The molar electronic entropy is R times the logarithm of G naught, because the electronic Partition function is approximately G naught. G naught is just 1 for helium. So if we look at the molar entropy for the electronic energy levels of helium, it's 0. Mostly it's because all helium atoms are in the ground electronic state. I think 99.999999% of helium is in the ground electronic state. And therefore the entropy is just 0 regarding its electronic distribution. The electronic entropy of helium is simply 0. Usually if you look at any other chemical with a singlet ground electronic state, its entropy is usually just 0. Unless, with rare exceptions, this chemical has some excited states only slightly above the ground electronic state. Now let's look at some molecules. When we look at molecules, we have translational modes, rotational modes, vibrational modes, and electronic modes. This part is usually 0, but for completion, so we still include these 4 terms here. Now let's look at HCl, for example. Let's say HCl35. We can calculate its molar translational entropy. It's 153.5. The calculation is a little interesting here. I'm comparing the translational entropy of HCl with the translational entropy of helium. There's a reason I do this. Let's go back to the previous page. Okay, now if you look at this equation, you can see between HCl and helium, if you compare HCl and helium, the only difference is this m. Also, if you look at this equation, same thing. The only difference is this molar mass between helium and HCl. So they should just differ by like 1.5 times the logarithm of mass 1 minus the logarithm of mass 2, and then multiply by R. That's it, because all other terms are the same. If we're looking at the same temperature, room temperature, 1 bar condition. Look, 1 bar condition, same temperature, they only differ by molar mass. And our plugging 1.5 Ln molar mass here, 1.5 Ln molar mass for helium, we got the difference. So the difference is 27.4 joule per mole per Kelvin. So the molar translational entropy of HCl is greater than the molar translational entropy of helium, only because HCl is heavier. And again, why is that? Since HCl is heavier, the translational energy spacings are smaller for HCl. So you can have a kind of more wild distribution of those molecules in more translational energy levels in HCl. Now let's look at the translational molar entropy of HCl. It's 27.4, more than helium. So I sum it up, I got 153.5 joule per mole per Kelvin. Now let's look at the rotational entropy. Here's the equation. We're going to just use this equation over here. dlnq over dt is simply 1 over t. And 1 over t times t is just 1. So there's only 1 here. And over here, the rotational Pauling function is kBt over hcb. The symmetry factor sigma is just 1, because this molecule does not have an inversion center. So hcb is h bar squared over 2I. I is the moment of inertia, and I is mu r squared. So we have all these equations. H bar is h over 2 pi. So that's why you see a bunch of pi on top. And now we can just evaluate this. Before we do this, this mu is m1 m2 over m1 plus m2, lowercase m. I want to convert it to uppercase m, so we multiply this mu by Avogadro constant. And then that's why you see Avogadro constant on the bottom. And also, there's a kb. I want to replace that with r, so you have a second Avogadro constant here. Now we can just plug in all the numbers to get the rotational molar entropy for HCl. It's just R is 8.3 and then 8 pi. The molar mass for hydrogen is 0.001 kilogram per mole. For chlorine, I think it's 0.035 kilogram per mole. Plug those numbers in. The equilibrium bond distance, you can look it up. It's 1.275 angstroms. Plug it in. Plug in R. Plug in temperature, assuming we're talking about room temperature. And we can do the calculation. You get 33 joule per mole per Kelvin. So we've got translational entropy. We got rotational entropy for 1 mole HCl. What about the vibrational entropy, electronic entropy? First, let's look at the vibrational entropy. First, let's use the 0 point vibrational energy as the zero reference. The molar vibrational entropy of HCl at temperature T is this. It's really complicated. It's R times T times d Ln Q over dt plus Ln Q. And we can evaluate this. We'll put negative sign here so that we can flip this up. We can flip this up. Now we take the derivative, the logarithm of something. It's going to be the reciprocal of this. And then we use chain rule. What's the derivative of this? You have this function over here. And then what's the derivative of this? You get something here. Alright, and then we clean it up. From here to here, it's just algebra. From this term to this term, we just multiply both the top and bottom by e to the power of positive h nu kBt. And then we got this minus 1 on top. This just disappears. we have t over t squared, so it's going to be just kBt over here, and then we copy the logarithm here. Why negative? Okay, it's just negative, negative, you get positive, negative, positive, you get negative. We can see h nu over kBt everywhere, here, here, and here. So it's a lot easier if we pre-calculate at least h nu over kb. Alright, h nu over kb is this, hc over lambda over kb, and this is 1 over lambda. You plug in all the numbers. H nu over kb is 4,200. And actually this has a unit. The unit of this is Kelvin. Sorry about missing the unit. It's actually in Kelvin, and usually for a unit we use regular font. We use italic font for variables. Now at room temperature we have this h nu over kb divided by room temperature, we get roughly 14, and this is unitless. Now I'm going to plug in 14 here, e to the power 14 minus 1, logarithm of 1 minus e to the power of negative 14, so we get this expression. We don't even have to calculate this because e to the power 14 is huge. 14 over that, it's really small, and this part is really close to Ln1, and Ln1 is 0. Therefore, the vibrational molar entropy for HCl is just 0. The molar vibrational entropy for this molecule at room temperature is this. It's roughly 0. This result is expected because nearly all HCl molecules occupy the same lowest vibrational energy level at room temperature. So more than 99.9999% HCl occupy the lowest vibrational energy level. There's really no disorder. Therefore, the molar vibrational entropy is just 0 or very close to 0 at room temperature or even higher temperatures. Usually you can say it's 0 unless the temperature is really high. On a side note, for molecules with low vibrational frequencies such as CO2 at room temperature, h nu over kBt is only 2.7. So remember, for HCl, h nu over kBt is 14, but for chlorine 2 at room temperature it's only 2.7. And in this case, the vibrational entropy can be more significant. We'll just replace 14 with 2.7. We get this formula. It's roughly 2.2 joule per mole Kelvin. It's still small. It's smaller than the translational and rotational entropy, but if you really want accurate molar entropy for chlorine 2, you probably want to take this 2.2 into account. The molar electronic entropy of HCl is 0 because pretty much all HCl molecules occupy the same singlet ground electronic state. So G0 is simply 1. The multiplicity of a singlet spin state is just 1. Singlet means 1. In total, the molar entropy of HCl35 at room temperature and 1 bar pressure is this. The molar translational entropy, the molar rotational entropy, and then we have vibration and electronic. These two are just 0. For translation, we have this number. For rotation, we have this number, 33. So in total, we have 186.5 joule per mole per Kelvin. Now, why do I specify chlorine 35? Because if you use chlorine 37, well, you will get slightly higher translational entropy and a slightly higher rotational entropy as well. So this number is for chlorine 35. For chlorine 37, you'll get a slightly higher molar entropy. Now the literature value of the entropy of HCl is 186.9. Look at these two numbers. They are pretty close to each other. These two numbers are obtained for room temperature and 1 bar pressure. 186.5 is our theoretical calculation. 186.9 is the experimental value. Theory and experiments agree with each other.
I didn't get that. Could you try again?
Similarly, we can hand calculate the molar entropy of any gas. And we can even calculate the molar entropy of a liquid or solid, given their partition function. For liquid or solid, it's hard to predict the molar entropy because it's a little hard to get the partition function right. In a liquid or solid, every single particle feels attraction and repulsion from surrounding particles, and it's hard to get the potential energy right. But if you do have the Q, you can hand calculate the molar entropy even for liquids and solids using this equation. Again, the molar entropy is simply the sum of four components: translational, rotational, vibrational, and electronic. Given the ideal gas approximation, the translational partition function is this: 2 pi m kBt to the power 1.5 times the volume of the container over Planck constant cubed. With the rigid rotor, that means the radius is constant. Rigid rotor approximation, harmonic oscillator approximation, that means the vibrational energy levels are n plus 1/2 times h nu, and that means the 0 point vibrational energy is 1/2 h nu. We can get the partition functions for rotation and for vibration. Rotation is here. If you have a linear molecule, it's kBt over sigma hcb. Sigma is the symmetry factor. B is the rotational constant. For a nonlinear molecule, it's square root of pi over sigma. We didn't derive this. Times the square root of kBt over hcb1, the square root of kBt over hcb2, times the square root of kBt over hcb3. For a linear molecule, we have 3n minus 5 vibrational modes. For a nonlinear molecule, we have 3n minus 6 vibrational modes. And the partition function is simply the product of 1 over 1 minus e to the power of negative h nu sub I times beta. So this nu sub I is the frequency of the ith vibrational modes. The electronic partition function is approximately G0. G0 is the degeneracy of the ground electronic state. The value of G0 depends on the electronic state. If you just have like helium, neon, H2, nitrogen 2, G0 is just 1. But if you have a doublet ground electronic state, G0 is 2. For oxygen gas in air, well, it's actually a triplet electronic state. So G sub 0 is 3. Chapter 25, Statistical Thermodynamics, Section 25.8, Helmholtz energy and Gibbs energy. The average energy of the particles in the MVT ensemble can be calculated using these equations. The average energy is equal to negative dlnq over d beta, or kBt squared dlnq over dt, or kBt dlnq over dlnt. The internal energy of the system relative to the 0K internal energy is this. It's N, the number of particles, times the average energy over here. So it's N times kBt squared dlnq over dt. And because N times kB is nr, so we have this expression as well. And also, we can write U relative to 0K internal energy is nRT times dlnq over dlnt. This comes from this expression times the number of particles. So now we can write this equation. The internal energy of a system minus its 0K internal energy is equal to nRT times dlnq over dlnt. So this is the so-called thermal correction to the internal energy. This is always positive. U at 0K is the sum of the ground electronic energy, which includes the nucleus repulsion, and also the 0-point vibrational energy. We have also derived this expression for entropy. Entropy is equal to Nr times dlnq over dlnt plus lnq. Given U, given S, we can get the expression of the Helmholtz energy of the system. So A minus the internal energy at 0K is U minus Ts minus the 0K internal energy. And we have this, which is nRT times dlnq over dlnt right here, and minus Ts. Ts is equal to nRT times the sum of these two terms. One is dlnq over dlnt, the other is lnq. So we have 1, 2, 3 terms, but the first and second terms cancel. So the result is really simple. The Helmholtz energy of a system minus the 0K internal energy is negative nRT lnq. And we have this equation here. Now look at this equation and this equation. They are pretty simple. U minus 0K internal energy is nRT times dlnq over dlnt. A minus 0K internal energy is negative nRT lnq. Helmholtz energy can be expressed in terms of the partition functions. A minus 0K internal energy is simply negative nRT lnq, and because Q is the product of translational, rotational, vibrational, and electronic partition functions, we can express lnq in terms of the sum of these 4 components. Now, because dA is negative SdT minus PdV from thermodynamics, we know pressure is negative delta A over delta V under constant temperature. And then this is equal to nRT, come from here, times, well, the first derivative of the sum of lnq trans, lnq rot, lnq vibration, lnq electronic on top with respect to volume under constant temperature condition. And this equation for pressure can be used to derive the ideal gas law. Now let's look at ideal gases. For ideal gas, we can get the expression for the translational, rotational, vibrational, and electronic partition functions. The last 3 components do not depend on volume at all. So if you take the derivative of Q rot over delta V, it's 0. The derivative of Ln vibrational partition function over delta V, it's 0. And the derivative of the logarithm of electronic partition function with respect to volume, also 0. And therefore, we only have the first term left. Now pressure is just nRT times the first derivative of the logarithm of the translational partition function. And for ideal gas, we know its translational partition function. It's 2 pi mkBT to the power of 1.5 times volume over the Planck constant cubed. And this logarithm can be separated into the logarithm of V plus the logarithm of everything else. Everything else does not depend on V, and therefore we have only the first derivative of the logarithm of V, which is 1 over V. So this whole thing is just 1 over V, and therefore P is nRT over V. PV equals nRT. We can also derive the expressions for enthalpy and Gibbs energy accordingly. So enthalpy minus the 0K internal energy is U plus PV minus 0K internal energy. And U minus U of 0K is nRT times dlnq over dlnt. And then plus PV, that's enthalpy. Gibbs energy minus the 0K internal energy. Well, because Gibbs energy is A plus PV, we have this expression, and we know A minus 0K internal energy is negative nRT lnq then G minus the internal energy at 0K is simply negative nRT ln Q plus PV. The 0K internal energy is the sum of the ground electronic energy and the 0 point vibration energy. In this ground electronic energy, the nucleus electrostatic repulsion is included. At 0K, note this: U equals H equals A equals G at 0K. Just because at 0K PV is 0, TS is also 0. Using the 0K internal energy as the 0 reference, we have these expressions, 5 of them. We have entropy, which is nR times the sum of two terms, d ln Q over d ln T, and ln Q, the sum of these two terms. We also have U minus 0K internal energy is nRT times d ln Q over d ln T. Helmholtz energy minus 0K internal energy is negative nRT times ln Q. Enthalpy minus 0K internal energy is nRT times d ln Q over d ln T plus PV. Yeah, just because H and U differ by PV. G minus 0K internal energy is negative nRT ln Q plus PV, just because G and A differ by PV. For monatomic ideal gases, we have a really simple expression for Q. Q is simply the translational Pauling function times the electronic Pauling function. The translational Pauling function is 2 pi m kBT to the power of 1.5 times the volume over Planck constant cubed. The electronic Pauling function is G sub 0, assuming we can ignore the excited states. For linear molecules that behave ideally in the gas phase, given the rigid rotor approximation and the harmonic oscillator approximation, Q is Q trans times Q of rotation times Q of vibration times Q of electronic. And then we have the translational Pauling function here, 2 pi m kBT to the power of 1.5 times volume over Planck constant cubed. The rotational Pauling function is kBT over sigma HCB. Sigma is the symmetry factor. B is the rotational constant. H times C times B equals h bar squared over 2I, where I is the moment of inertia. And now we have the vibrational Pauling function. We have 3 n minus 5 vibrational modes. For each vibrational mode, this is the Pauling function, 1 over 1 minus e to the power of negative h nu sub I beta. Nu sub I is the frequency of the ith vibrational mode. Beta is 1 over kBT. Finally, the electronic Pauling function is assumed to be just G sub 0. For nonlinear ideal gas molecules, the expression of Q is as follows. We have the same translational Pauling function, but the rotational Pauling function looks different. It's the square root of pi over sigma, and then square root of kBT over HCB1, square root of kBT over HCB2, square root of kBT over HCB3. B1, B2, B3 are the rotational constants. And then the product of all those vibrational modes, 1 over 1 minus e to the power of h nu sub I beta. Nu sub I is the vibrational frequency of the ith vibrational mode, and the beta is kBT. Finally, G0 is the electronic Pauling function. It's G0 assuming the first excited state minus the ground excited state. The difference is much greater than kBT, so we can ignore the excited states. So this is how we get Q for atoms, for linear molecules, and for nonlinear molecules. Once we have the expression of Q, we just plug in Q here, 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 and here. We will be able to get the expressions for entropy, internal energy, Helmholtz energy, enthalpy, and Gibbs energy. Now get back to the wheel of thermodynamics. A is U is A plus TS, A is H minus PV. H is U plus PV, H is G plus TS. G is H minus TS, G is A plus PV, A is G minus PV, A is U minus TS. And also, we can have expressions of U, H, A, and G relative to the 0K internal energy. For U, it's nRT times d Ln(q) over d Ln(t). For A, it's negative nRT Ln(q) relative to 0K internal energy. H is simply PV plus U, and G is simply A plus PV. So we have this will of thermodynamics. And again, to determine those thermodynamic functions, all we need is the expression of Q, the partition function of the system. And Q is equal to the product of translational partition function, rotational partition function, vibrational partition function, and electronic partition function. Chapter 25, Statistical Thermodynamics. Section 25.9, Thermodynamics and Chemical Kinetics. For a general chemical reaction from reactants J and K to products L and M, assuming the coefficients are A, B, and C and D, we can write out the expression for the standard Gibbs energy of reaction. It's C times the standard molar Gibbs energy of L plus D times the standard molar Gibbs energy of M, and then minus the molar Gibbs energy of J and K with the coefficients in the front. And because G minus the 0K internal energy is negative nRT Ln(q) plus PV, from the previous section, we have this equation: the standard molar Gibbs energy minus the 0K molar internal energy is equal to negative RT times the natural logarithm of the standard partition function plus PV sub M. This is the molar volume. Really, we just use this equation divided by the number of moles. Now we can use this equation for all reactants and all products. And then we can take the difference between the products and the reactants. We get the standard Gibbs energy of reaction is equal to the 0K internal energy of the reaction, and then minus RT, and over here we have the logarithms of the partition functions of the products minus the logarithms of the partition functions of the reactants. Also, we need to take care of the coefficients. And finally, we have a delta PV term. This is delta PVM, so this means molar or per mole reaction. So we have a really long expression over here. But again, we just need to take the difference between the reactants and the products for this term, for this term, and for this term. And also, we somehow need to take care of all those coefficients A, B, C, D in here. The A, B, C, D are included in here and also in here implicitly. And we have this equation from general chemistry. The natural logarithm of the equilibrium constant is negative standard Gibbs energy of reaction over RT. And this is this. We have three parts: the internal energy of reaction, the partition functions, and delta PV. So over here we have this 0K internal energy of reaction divided by negative RT over here, and this part is from this divided by negative RT, and finally delta PV over negative RT. So we get the expression of the logarithm of equilibrium constant K. So this equilibrium constant is equal to, well, over here again, partition function, the PV term, and the internal energy term. First, the partition function over here. You can see this equilibrium constant is proportional to the standard partition function of L to the power of C. So I copy that here. And then we have chemical M on top. Chemicals J and K are reactants. They appear on the bottom. And I took care of the coefficients A, B, C, and D. Now the PV term, we have this term. So e to the power of negative delta PV M over RT. This means per mole reaction. And finally, this term, we have e to the power of negative delta U of R at 0K over RT. Although we see this 0K here, it doesn't mean this T is 0K. This T can be any temperature. I put 0K here, only it means Well, we need to get the 0K internal energy for the products and the 0K internal energy of the reactants, and then take the difference there. The 0K internal energy is the sum of the electronic energy and the 0-point vibration energy. Now let's look at this term again. So those are standard partition functions for L, M, J, and K. So I'm using X here to denote L, M, J, or K. So over here, this is just partition function of just one more X in the standard state. Sorry about the typo, this should be X. This is the function of temperature. And again, the 0K internal energy is the sum of the electronic energy and the 0-point vibration energy. The electronic energy includes the nucleus repulsion just for convenience. Otherwise, we'll have to say electronic energy plus nucleus repulsion plus 0-point vibration energy. And this is used as the reference when the partition function is derived or computed. Mostly when we derive the vibrational partition function and electronic partition function, we use the energy of the ground electronic state as the zero reference. We use the 0-point vibration energy as the zero reference. So again, this is the internal energy of the reaction at 0K. It's just we take the difference between the products and reactants. For the delta PV term per mole reaction, usually we just use approximation here. It's roughly RT times the change in the number of gases in the chemical reaction. So if you have 3 here in front of a gas, you have 2 in front of another gas on the other side, then delta N gases is just -1, it's 2 minus 3. You don't have to worry about solids or liquids. In chemical kinetics, the reaction rate constant K can be easily derived for unimolecular reactions in the gas phase, assuming the equilibrium between the transition state and the reactant. So the concentration of the transition state divided by the concentration of the reactant is this. Where does this come from? It comes from the previous equation over here. So we have a really complex equation over here, assuming there are 2 products, 2 reactants. But what if these 2 are replaced by the transition state, and these 2 are replaced with the reactants? And then we got this equation here. It's just Q of the transition state over the Q of reactant. And we copy this term, we copy this term. Double dagger usually means transition state is involved, and then you see double dagger. Whenever you see double dagger, that means transition state. Now let's look at the rate constant of a transition state structure being converted to products. Well, if you have a transition state already, it has a higher energy than the product. Supposedly it's going to just go down the hill, but it still takes time. So the rate constant for this is approximately kBT over H. Kb is Boltzmann constant, T is temperature, H is Planck constant. We're going to prove this in a semi-quantitative manner. We're going to treat the transformation from the transition state to the product as if it were a particle in a box. So I drew a box over here, so a particle can move around. Now we have the momentum of the motion for the transformation using the de Broglie relation. So this is momentum, mv is h over lambda, and lambda is approximately a, the length of the box. So mv is approximately h over a semi-quantitatively. A is the length of the box. And now I'm going to use this equation in kinetics. Roughly 1/2 mv squared is 1/2 kBt. So in this single dimension, we're going to assume the average kinetic energy is 1/2 kBt, just like the average translational energy or average rotational energy. Now we have 2 equations, these 2 equations. I'm going to use the second equation divided by the first equation. So 1/2 mv squared over mv here, 1/2 kBt over this here. Now we have this equation, 1/2 and 1/2 cancel. mv squared over mv, that's just v. And we need to flip a to top. And we reorganize this equation, then a over v is h over kBt. So again, this a over v is going to be h over kBt. We have proven this. A over v is h over kBt. A is the length of the box, particle in the box problem, and v is the speed of the particle, or a and v are the length or distance and the speed of the transformation from the transition state to the products. Just assume that from the transition state to the product, you need a particle to move a certain distance a with a speed v. So a over v is the time period for the transformation from the transition state to the product. And therefore, if we take the reciprocal of this a over v, that's kBt over h. That's the frequency of the transformation. And also we have this equation. We have the concentration of transition state over the concentration of the reactant. When they are at equilibrium, it's the ratio between the partition functions, and then e to the power of negative delta pvm over rt, e to the power of negative delta um over rt. So we have this equation that allows us to estimate the concentration of the transition state. So now the reaction rate is this. We need the concentration of the transition state multiplied by the frequency of the transformation, which is kBt over h. We plug in this equation here. Ts is simply R times all this. So the reaction rate is kBt over h times the concentration of the reactant times the ratio between the partition function of the transition state and the partition function of the reactant. And then e to the power of negative delta pvm over rt, e to the power of negative delta um over rt. And this is 0k internal energy. And therefore, the reaction rate constant K is this reaction rate divided by the concentration of R. And we have this kBt over h, the ratio between the partition functions of the transition state versus reactants, e to the power of negative delta pvm over rt, e to the power of negative this is 0k internal energy of reaction over RT. And now we transform this ratio. The Q of TS over the Q of reactant is equal to e to the power of ln Q of transition state over e to the power of ln Q of reactant. So it's e to the power of delta ln Q double dagger. So over here, this delta ln Q double dagger is ln Q of the transition state minus ln Q of reactant over here. And then we have a simplified equation for rate constant K. K is kBt over h, e to the power of delta ln Q double dagger, e to the power of negative delta pvm over rt, e to the power of negative 0k internal energy of reaction over rt. This is fairly complex. We have three exponential functions, but we can prove this. We can combine the three exponential functions, and essentially it's going to be just e to the power of negative. Over here, Gibbs energy of activation over RT. So really, we need to combine this, this, and this to get negative Gibbs energy of activation over RT. Alright, so we're going to copy this in the next page. It's right here. The rate constant K for a unimolecular reaction is this: kBt over h, e to the power of delta ln Q double dagger, e to the power of negative delta PV double dagger per mole reaction over RT, and then e to the power of negative 0k internal energy of reaction over RT. Really complicated, but this equation is the same as the Irene equation. K is just kBt over h times e to the power of negative Gibbs energy of activation over RT. And here's the proof. So remember, A minus the 0k internal energy is negative nRT times ln Q. So A is simply this 0k internal energy minus nRT times ln Q. We can use this equation for both the reactant and for the transition state, and then take the difference between the reactant and the transition state. So we're going to use transition state minus reactant. So delta A double dagger, that's the difference, is equal to, well, over here, this is the difference in the 0k internal energy from the reactant to the transition state. So really, this part is also transition state minus the reactant. And okay, finally here, we have negative RT delta ln Q double dagger. Delta ln Q double dagger is the Q of the transition state minus the Q of the reactant. Alright, so we have this. Again, over here, this equation, this notation is the molar 0K internal energy difference between the transition state and the reactant. Alright, so it's the change of the 0K internal energy from the reactant to the transition state per mole reaction at 0K. At 0K, that means we have just the ground electronic state energy plus the 0 point vibrational energy. Alright, now starting from this equation, I think I see this negative delta U double dagger. I see this delta L and Q. I'll put these two together this way. Alright, delta U and this delta L and Q are put together. And because this delta U is divided by RT, this delta L and Q is not divided by RT. So I need to multiply the delta L and Q by RT in here, and then finally divide by RT. Now look at this expression enclosed in the square parenthesis. Over here, this 2 is simply negative delta A double dagger. So this whole thing is negative delta A double dagger because this part is this with the opposite sign. This part, RT times delta L and Q, is this with the opposite sign. Alright, so this is how we simplify this term, the first exponential function and the third exponential function. You combine them, you put them together, and you can see this 2 is simply negative Helmholtz energy of activation. And now we have only 2 exponential functions left. The rate constant is kBt over h times e to the power of negative Helmholtz energy of activation over RT, and e to the power of negative delta PV per mole reaction over RT. And this double dagger means we're going to use transition state minus the reactant. Now we finally combine these 2 exponential functions. We can put these 2 together. Alright, so this and this together divided by RT, that's a common factor. Negative sign, that's a common factor. So we have this in the pair of square bracket. We have delta A plus delta PV. And what is that? Because G is A plus PV, so delta A plus delta PV is simply delta G. We just proved the reaction rate constant for a unimolecular reaction is kBt over h times e to the power of negative Gibbs energy of activation over RT. Again, because G is A plus PV, delta G is delta A plus PV, delta G double dagger is delta A plus PV double dagger, and then this is delta A double dagger plus delta PV double dagger over here. Alright? And again, delta PV sub M is the change of PV from the reactant to the transition state per mole reaction at temperature T. Now in the end, we proved the Irene equation. The rate constant is kBt over h times e to the power of negative Gibbs energy of activation over RT. Statistical thermodynamics ends up with some fundamental equations, such as this Irene equation in thermodynamics and chemical kinetics.